Well, hello, my fellow AC techs, and welcome back to HV 120. We're going to be talking about the installation of air conditioning units and really as it deals with the residential side of the system, different airflows that we'll be going through, the reason why manufacturers have manufacturer training, um, ductwork designs, installation of the ductwork, different ways that we move that air through there, and the remembrance that we are running 400 CFMs per ton of refrigeration within our system. We'll be going through quite a few different fittings, talking about the different ways that we're going to be moving that air into the system, the installation of that mastic, the cutting of the ductwork, and the installation of the pieces of the fittings, the takeoffs, the 90s uh, into the ductwork, the sealing of the ductwork, the putting together of certain round pipes, boots, 90s collars, and so forth. But we'll be hitting all aspects of the installation of an air conditioning system tonight. So manufacturers have an issue, and that issue is with the installers. They have no control over who is installing their piece of equipment. So the final installation comes down to individuals who have been trained, maybe not by the factories themselves, but possibly by other technicians that are in the field. I'm currently on a series called They Can Learn That in the Field, and different ways that technicians are learning the wrong ways to install AC systems in the field, such as only pulling 30-minute vacuums and not going over the checklist that the manufacturer gives us. There is a reason that the manufacturer provides for us an installation manual for the AC systems that they are providing to us. It's because they want our systems to be installed in a particular way. Now, if we aren't installing those systems in a particular way, then those systems will not last the 15 to 20 years that the manufacturer is uh, saying that those systems are going to last. Manufacturers provide warranties on new equipment that is being installed. Those warranties could be voided if the proper procedures by the technician are not followed. Many examples of technicians installing pieces of equipment that are not following the proper procedures. The actual manufacturer does not have to warranty any of the parts on those systems, so it would fall back on the installers of those piece of equipment or the company that installed that piece of equipment because they didn't follow the proper manufacturer suggested the manufacturers provided instructions about how to install their systems. And I am specifically talking about airflow, and I am specifically talking about refrigerant line sizes running from the condensing unit on the outdoor to the evaporator on the indoor. Airflow, as it pertains to the correct installation and measurement of the ductwork that's in that system. So that's what installers are going to have to do. Read the manuals, and you'll know exactly how to install the AC to per the manufacturer's recommendations. Now, with that being said, bad installs do happen by individuals, and you will hear when you get out in the field that certain individuals do not like certain pieces of equipment, whether that is a Carrier or Bryant or Trane American Standard, Rheem or Rude. They will develop opinions of those pieces of equipment. And I can just tell you that all these manufacturers are getting their parts from the same distributors, and they're installing the same parts that other manufacturers are installing. So what's it come down to? It comes down to the installer doing the correct installation of the piece of equipment. And because the installers are not doing the correct manufactured recommendations for the piece of equipment, that piece of equipment will get a bad name. And that is completely. There are systems out there that yes, they are made for economy, and they are not made to last very long within the system itself. But for the majority of the systems that are out there, bad equipment names come from bad installers. Now, the installation of an air conditioning system actually requires the individual to know three different trades. Not only the heating, ventilation, and air conditioning trade, but the electrical trade, and then to be mechanically minded as well for installation of that system. So installing an air conditioner will require you to understand ductwork, assembling that ductwork together, uh, measuring that ductwork to make sure you're getting the proper airflow and static pressure within that system, total pressure and velocity pressure off of that duct. You will also have to understand the supporting aspect of it as you're running different types of duct board, flex duct, metal duct within that system. You will also know the requirements for insulating that piece of equipment to keep it from condensating and to keep it from damaging other structures that are nearby to the ductwork. So another trade that you will have to understand is the electrical trade. You'll have to wire it low voltage wire up to that unit, depending on the location that you are, which state that you are in. You might be running the high voltage, or local codes might prohibit you from opening up the electric box. But for most of rural America, you will be opening up the electric box and you will be hooking up the electric to the breaker box to run for the outdoor unit and also the indoor unit, especially on remodel applications or you're replacing certain pieces of equipment that are out there. We can't always rely on electricians to come and work on those things. Many times it falls under the HVAC contractor's responsibility to run the proper electric in that case. And then mechanically, you have to be able to braze. And I know there's a lot of individuals out there. I don't have to braze anymore because we have this thing called Zoom lock. I'll tell you now that any person can push a button and can seal up a refrigeration line. But when it comes to actually fixing a refrigeration coil or brazing systems that are properly done with purging of nitrogen and stuff, you cannot replace a technician that has that type of skill. Plus, that's a skill that you can use in any other situation in your life. So I recommend that you do learn how to braze and solder because you will be running into aspects of that within your field, but also within your life as far as your housing or if you're going to be running lines for other individuals. Condensate lines, so we are dealing with plumbing, the setting of the equipment, and some of this equipment can be very large, so we're going to be working with a lot of large machinery to move this equipment around and then to hook it up inside of the house or inside of the factory or inside of the commercial building. So those are the three aspects of installation that an HVAC technician is going to have to learn. I always like to refer that HVAC is the best of all the trades, because not only do we get to know about our trade, but we get to know about the electrician's trade and we get to know about the plumber's trade as well, the mechanical aspect of it. So you are going to be a jack of all trades, master of one trade. Well, the next thing we're going to be discussing is the ductwork within the air conditioning system. We're going to be talking about the different designs of ductwork that we're going to be seeing. And those different designs of ductwork that we're going to be seeing: rectangular metal, round metal, fiberglass, ductboard, which I am not a big fan of fiberglass ductboard. I'm not going to say it on the video for reasons. I don't like having that fiberglass in the airstream itself. Flex duct is another way that we can run air to certain areas inside of the house. So those are the couple of different systems that you're going to be running, or I'm sorry, different materials that you're going to be running for the air distribution for an air conditioning system. So the installation of metal ductwork or rectangular ductwork, that is, it can either be prefabbed bought from the manufacturer, or we can take these things and actually bend up the ductwork ourselves. To save time, manufacturers have produced common sizes when it comes to the ductwork. It's that to the ductwork. They've fabricated the sheet metal in a certain way. One side of the ductwork has a Pittsburgh on it, and then we'll place those two pieces together to give us a nice rectangular ductwork that our airflow will go through. For the most part, the gauge of the ductwork is running somewhere between 26 and 22 gauge metal. The thicker the gauge of the metal, the more rigidity it has and its ability to withstand popping noises on it. If we were to go with a really thin metal, we would end up hearing a lot of popping noises off our ductwork, as the total pressure of the system was to build within that ductwork itself as we're moving air throughout it. The metal duct is very durable in that it can withstand rodents, mice from trying to dig into it, but our flex duct and our fiberboard duct is not very good for resisting rodents in a way, because they can get into it if they really wanted to get to the warmth that is behind that ductwork. Now, they're not going to be able to, once they get through the insulation that is around the metal ductwork, well, heck, they're not getting through that metal at all. So that's why I like to run for my main trunks this metal duct. Very rigid, very durable. Now, when we're putting these two pieces of ductwork together, as shown in the picture that is behind the words there, you will see a connector called an S-lock connector. That S-lock connector is going to fit in between the two pieces of ductwork. So in this location right here, running along the ductwork, we're going to have that S-lock. So as you can see, that's where the S-lock is going to be located. One piece of ductwork will have the S-lock on it, and the other piece of ductwork will not. Now, as we are depicting in this picture at the top, we can see that one side of the rectangular ductwork will fit into the top side of the S-lock, and the other rectangular ductwork will fit into the bottom side of the S-lock that's up there. So as we're looking at it, here's your one side of your ductwork, and then here's the other side of the ductwork itself as they are fitting together. We will also provide drive cleats that will go on the sides, or the shorter sides of the ductwork itself. I'm going to circle the ductwork and show you where it's at, and I'm also, in the next slide, we'll go over what the drives look like on that piece of ductwork and get into a little bit more detail about how we're sliding those two pieces of ductwork together and then firming them up with the drive cleats that are on there. That is your S-lock, and that is your drive cleats right there. So this is just another picture of the drive cleat, which is in the red arrow. Okay, so this is my drive cleat right there, as you guys can see. That's my drive cleat. And then my S-lock is right there. There's my S-lock. Okay, the arrows are actually going to be showing you the different areas that those fittings are going to be placed on the rectangular ductwork so that we can put that ductwork together. The reason that we need to put that ductwork together is our air handler is many, many feet away from the actual rooms in which we want to condition. So we will take pieces of ductwork and we will extend out our air into an environment so that we can provide air to different rooms at the same pressure, at the same velocity that system needs to cool that place down or to heat that place up. So once again, here's your S-lock, okay, and then once again up here, here's your drive cleat. After we get done putting our drive cleats on the shorter side of the ductwork, we will bend those little tabs over the ductwork itself. Now, the purpose of the bending of those little tabs over the ductwork is so that we are securing that ductwork in place. Some people After they get done doing that, we'll put screws in top of those, and that's just going to firm up that drive cleat and the connection that has to the ductwork itself. I recommend not to do that. I've actually seen ductwork separate out from doing that, especially if you're putting it on the shorter side of the ductwork. I would stick with the drive cleats, bend them over, and then we'll talk later about how we're going to seal that individual, because that is not an airtight seal. So we need an airtight seal, because 30%, 20 to 30% of the air that's going through this ductwork, if you do not seal it, will be forced out of the cracks that are in this ductwork into unconditioned spaces. And really, that's just taking money and throwing it down the drain. Now, as we are spanning the metal duct and we're running that metal duct along the joists of the floor, or if we're going to be running it in the ceiling, we're also going to be running along the joists of the ceiling. If we're hanging this ductwork, we want to hang it every 3 to 4 feet. We want to put straps. Now, I usually use some of the drive cleats that we used back when we were connecting the two rectangular pipes together. I use those drive cleats as well to hang the ductwork on those floor joists as we're running them along the along the basement and or the crawl space of that place. We could use strapping material. We can use drive cleats. We can use S-lock. We can use any of the different types of connectors for our rectangular duct to hang that duct into the air. Perforated strap is another hanging material that we can use. But the whole purpose of it is to support that weight that's on that ductwork so it doesn't fall down. You might not think about it, but metal duct can get quite heavy as we're running along it. Another thing that we're going to have to worry about for our metal ductwork is the sealing of that duct. Now I'm talking about the gaps that come together with where our drive cleats are and where our S-lock is. That air will leak out of there. Also the Pittsburgh, which is the joining of the two pieces of metal together to make our square duct, will also leak, and we want to put mastic on that as well. And mastic, all you can think about is mastic as caulk on a brush. That's what mastic is. So when we talk about the actual ductwork on our system, we're referring to rectangular duct. 30% of the air that we condition, if we don't seal our ductwork up, will be lost to the unconditioned space. So 30% of the ductwork, if we're not sealing that ductwork up or we're not insulating that ductwork properly, could be lost to other conditions that we don't want to happen. So this would be wasted money, wasted energy that we're putting into unconditioned spaces in that environment. So it's important for us to seal that ductwork up with mastic. Now your rectangular ductwork is going to have gaps in it, and those gaps are going to be evident where we're putting the two pieces of metal ductwork together. Now I know that we're using drive cleats on there, and we are actually, when these two things are coming together, we'll have these two pieces of ductwork sitting here. We'll have drive cleats and S-lock, they'll actually overlap a tad bit on them, and then we'll have our drive cleats that are going in here with the tabs that are bent over on our drive cleats. We will take mastic, which is basically caulk on a brush, and we will brush that joint with that silicone looking material, and it will cause a airtight seal to form within that ductwork, so we don't have to worry about that 30% loss in the ductwork as far as air leakage is concerned. As we do this, it's going to increase our static pressure on our system so that we can forcibly put the air into the environment that we want to condition. So that's a positive to it. Ductwork has to be measured correctly with the appropriate length on our ductwork to get the appropriate static pressure on our ductwork as well. Now, when we refer to ductwork, the shorter side of the ductwork, for the most part, is going to be manufactured, and we're going to purchase it, and it's going to be 8 inches in length. So the shorter side is 8 inches. Now you can figure all of your rectangular duct by that the system will be 8 inches in depth for that. Now the length of that particular ductwork, we can run it anywhere from 8 inches all the way to 24 inches, and even larger than that in some commercial applications for our ductwork. So our square ductwork that's going to be sitting on there, it's going to be referred to as 8 inches by, and then we'll use the length of that 8 by 16 ductwork as we're using it within our system to move that air along it. Most of the ductwork is going to be sold at the supply store, so go ahead and pick that up there and look at it as we're going out there. Now, what we end up having is our furnaces are going to create some sort of vibration on our ductwork. And as we come off of our ductwork with a transition, which we'll discuss later on, that transition to cut down on the vibrations of the actual furnace, we're going to put in a flexible connector between the takeoff and the actual square duct that's running in there. And this is a type of canvas connector that will absorb the vibrations off of the furnace so that we are not transmitting the vibration and the noise down the entire stretch of ductwork on that system. And then we'll go ahead and we'll hook it up to our ductwork as it's running down it. So that is a canvas connector right there on our particular ductwork, and it's there to stop the vibrations from the furnace from entering into the ductwork and running down and into the environment in which our occupants are there. So as we begin to talk about the parts that make up the air distribution system, there's a couple of things that we have to understand about it. First off, we have some sort of air handler in our system. Now that air handler is going to have some sort of fan attached to it that's going to be moving that air over the system. We're going to have a return to that system, which is indicated by the R, and then we're going to have a supply in that system, which is going to be indicated by the S that's on that. Now, this is your air handler right here. Your air handler could be a furnace, or it could just be a fan coil with it could be a fan coil with an evaporator on the inside of it. Now, if it is a furnace, the next item that we're going to have on that furnace is some sort of boxed air coil on it. So the furnace is going to have that A coil on top of it with a fan coil that's going to sit there. Now off of that, we are going to run a plenum. That plenum is just an extension of the air that's coming off of the furnace. And off of that plenum, we are going to run what we call a takeoff. That takeoff is going to be what is going to take the main air and distribute it off of the plenum itself. So what we'll do is we'll come in here and we'll cut a hole into our plenum in such a way. Then on that, we will attach a straight takeoff onto it so that we can take it from the plenum sides to an 8-inch ductwork. And this could be 8 inches right here on this ductwork. And then let's say that it just happens to be a 16. So in this area here would be the 16. So we would run an 8 by 16 ductwork off of that plenum so that we can distribute that air into the branches to the facility or the rooms that we want to heat or cool. Now, within this ductwork right here, which happens to be an 8 by 16 duct, we are going to put other takeoffs into that ductwork as well. A couple of rules that we have to understand about this ductwork. We are not to put takeoffs at the ends of our piping. Okay, because we have something called static pressure, total pressure, and velocity pressure that we need to build up within this ductwork so that we can distribute the air correctly over the entire thing. So we would come back 1 foot off of the ductwork at the end of it, at least 12 inches. Okay, and then we would put what we call another takeoff. Now that takeoff right there is going to be running into or in the vicinity of the outside wall, if we're talking about the supply temp, into something that we call a boot, and I'll talk about the boot later on. And the boot is what's going to house the register that's going to distribute the air throughout the entire room that's sitting there. Now, that is the basic design of an air conditioning system that's distributing air throughout the entire vicinity of it. I hope that I explained that well enough to you so that you understand what these next components are going to be for that. Now, this individual component right here is a takeoff. You see the feet that are on this. What we will do is inside of the plenum, we will cut a hole in the dimension of this takeoff. Now, when we put this takeoff in, these little ribs that are on the takeoff are going to look like this, and we're going to take them and we're going to bend them over the metal that's inside of that takeoff right there. Okay, so these little ribs are indicated right there. This is the metal, and then we'll take it and we'll bend it over that metal that's sitting on it, so that we can make a nice seal on that. Remember, anytime that you have a gap, you're going to want to put mastic on it as well. That way we can seal up that. Now, there's going to be drive cleats that we're going to be able to put on this takeoff assembly. There's also going to be S-lock on it that we can take that square duct and put it on there. There's transition takeoff assemblies, which go from a smaller size into a larger size. And there's also round one, square around type of takeoffs as well on our systems. So the takeoffs are what's going to come off of the plenum and move that air from the plenum into our boots, and we'll talk about those in a little bit. Now, takeoffs come in a variety of different applications. We can have the transition takeoffs where we are transitioning from one size to another, and that would be a square duct. And in my next slide, I'll show you that transition takeoff and the plenum on an actual installation that we have done. So square piping to round piping is an application, and that's a picture of it right behind us right there, where we're going from a square duct that's going to be going around like this into, as the air is flowing out, it's going to come into this round duct right here on that system. So that's just another takeoff that you will see. Now, what we are witnessing here is an installation of a furnace, an air conditioner. On this furnace and air conditioner, we have our plenum. Down here, towards the bottom side down here, this is where we're going to see our furnace. Our air handler or our furnace are going to be in that area itself. So this is going to be our furnace. Off of our furnace, we're going to run up this particular pipe, and that particular pipe is going to be known as the plenum. So that pipe that's sitting right there that encases also our coolant lines, as we can see right here. Here's our suction line and here's our liquid line, are going to be encased inside of that plenum itself. The plenum can extend off of the furnace as high as we'd like to run it, but there are limitations to the height of it. As the further we get away from the furnace, the more dissipation of the static pressure, total pressure, and velocity pressure will happen. So we want to try to keep that plenum relatively short as we can get it within reason. I would say at least 3 feet off of the top of the evaporator, and then extending out into our trunks that are going to distribute that air into the places where we want to put those we'll put that air. So here's our plenum. I talked about numerous different types of takeoffs that we will see on our systems. This one happens to be a transition type of takeoff. And if I was to draw this on the inside, we would see that the transition goes from a rectangular type of ductwork into what we like to look at as our 8-inch by 16, or this one just happens to be 20 inches in length for that. So that is a transition type of ductwork when we look at it. Our drive cleats will fit on the shorter side. Our S-lock will be on the longer side. As you can notice, I've taken those drive cleats and I have placed them on the joists on our system. And these tabs that are sitting right here on this system, I've actually bent them up and screwed them into that joist. So, I mean, we're going to bend over our tabs on that, and then we're going to screw them up. So I don't know if you can really see it right in there, but that tab, I bent it. That's the tab they usually bend over for the ductwork, and I'm going to put a screw in that, and it's going to give me a nice tight connection up against that joist. A lot of people don't like to run their joists like that, I mean their ductwork like that, because they're afraid of the vibration off of the unit being transferred into the joist. And then into the living environment of the individuals in there. Really haven't had an issue with that. If our furnace is vibrating that bad, then there's something else that we have to look at that's going to lead us to the problem of that vibration that's in there. The tabs that are on the bottom of the drive cleat, I will take that and put that on the bottom side of the ductwork so it holds it. And then I'll put another screw in that guy to hold the ductwork in place as we are hanging it along the joists every 3 to 4 feet for our rectangular ductwork. We're going to put hangers up and get them hooked up in there. I always like to see 2 hangers on a 5-foot ductwork. It helps with the weight distribution on the hangers, but also gives a good foundation to running that ductwork along it. Well, we talked about the canvas connector, as we can see on this particular picture. This is a canvas connector. Our S-lock is located in this area right here. And this is going to be hooked onto our square duct. And then we have our drive cleat that's going to go on this section right here for our canvas connector. And the canvas connector is there to stop vibrations from transferring from the air handling unit through the ductwork and into the living environment of individuals out there. Then we're continuing on with our installation of our gas furnace right here. We continue to run our plenum. This is our takeoff, transition takeoff. We see our different hangers that we put up for this furnace itself. Hangers right there and hangers right there. We'll take our squared around duct and we'll place it up there. And then we'll go along the actual seams of that ductwork and we'll put a special type of caulk on a brush, which is referred to as the mastic caulk. Very flexible, lasts for a very, very long time, longer than any tape would or any duct tape would on that particular unit. We see our plenum coming off of our furnace. Inside of this ductwork, we have placed the A coil right there, and it might come up just a tad bit higher. Might be right there, but on that, we have our suction line for our evaporator and our liquid line for our evaporator. Haven't put the flue pipes on this gas furnace yet, but you can see that we have attached our air bear filter to the side of it. So our return is going to come in this direction. We're going to condition that air. We're going to blow it up and out into the transition ductwork, and then coming straight at us, we're going to be running that squared around duct right down the line. As we continue to look at this system for air conditioning. So we talked about the mastic that's going to be going on our particular joints for our rectangular duct. Now, right in front of you is a drive cleat. So this right here is a drive cleat. And what we're going to do is we're going to paint the edges of that drive cleat, and we're going to seal that air inside the ductwork so that we can get, so we don't lose our money that we just put into conditioning that air itself. On the left-hand side, you can see the insulation that's on there. And after we got done putting that mastic type of material, that sealant type of material on that ductwork, we would go ahead and insulate it and then tape it. Tape the insulation, not the ductwork. Now that insulation that you're seeing there, right down in here, you can see it. It is foil back. Foil back insulation is great for a moisture barrier between the ductwork and the air that's on the outside of it. And the whole purpose of insulating it is to conserve energy, but also to prevent heat transfer from that ductwork to the air that's around it. And that vapor barrier is one of the most important parts of that entire encapsulation of the duct work itself. Now you can see we call it caulk on a brush, yes, because we are painting that actual fitting with caulking from the mastic itself that's sitting there on that. Apply it to the joint, makes an airtight seal. Do not use duct tape, do not use silver tape, do not use any type of uh, tape to seal up that particular air in there. The adhesive that is on that tape will not last over the course of that particular system. Okay, so what we're going to do now is we're going to go through the actual process of installing a branch run on the main trunk line that's running for the air conditioning or the furnace or any air distribution system that we can see. We got a couple of different parts that we are looking at when it comes to this. We are going to install a damper on the takeoff of this system. Now that damper is going to sit on the inside of the takeoff itself, and you can see that metal right there. This lever on the outside of the takeoff is what we're going to use to move that damper on the inside to adjust the airflow coming out of our branch ducts so that we can make sure to give the proper CFM value to that room in order to cool and in order to heat that room up. Now, we see these little tabs that are on the takeoff itself. What we're going to do is we're going to cut a hole inside of this piece of ductwork right here, and we have it marked right here, and we're going to cut a hole. We're going to mark it out using this takeoff because it's a good template for us to use. And then we're going to use some sort of aviation snips with some sort of cutter to get us into that ductwork. And then we're going to cut a circle out. But a couple of things to understand about what we're seeing within this picture. So this is a round takeoff. And on the inside of the takeoff, we have a damper. And this is what you need to know about every unit that you go to install, is that when we are taking off from the main trunk, we should install a damper in it in order to adjust the CFM values going into that particular branch. So installing the damper is as easy as drilling a hole into the takeoff that's sitting there. So I'll drill a hole on one side, and there's a lot of different dampers out there, and I'll draw a hole on the drill a hole on the other side, and then I'll insert that damper or that air volume control into the takeoff itself. Now, to get the takeoff onto the piece of metal or the trunk, what I'm going to do is flip it upside down so that the crimped edge is facing down. That's going to make sure they got a nice tight fitting when I put this ductwork in, when I put this takeoff in there, so I don't have a very big air gap that I'm going to have to fill up with my mastic caulk that I'm going to be putting on it later. So I'm drawing it out with a Sharpie, and I'm going to draw completely around that particular takeoff. And if it was a square takeoff, I would measure it just like I'm doing right now. I'd measure it for the cutting of the square hole, a square to round takeoff. And there's a lot of different takeoffs that we have out there. But what we're going to do here is we're going to trace out the takeoff onto the main trunk or the main plenum that's coming off of the furnace or the air handler, and then we are going to cut into that pipe itself. Well, continuing on our process, we can see that we have done a circle around the actual ductwork to show us exactly where these takeoffs are going to go. A couple of rules that you need to understand about the takeoffs. The takeoffs should not be at the end of the trunk. If the takeoffs are at the end of the trunk, we will lose the pressurization of that trunk to be able to push out evenly through all the distribution branches that are on this main trunk. So we want to come back at least a foot, 12 inches off of the end of a piece of pipe on the end, so that we can pressurize it, so we can get good static, good velocity, good total pressure within our ductwork, and that air will flow out evenly through all the different branch runs that are a part of it. Now I've done the circles for the takeoffs. I got my two takeoffs sitting down there. You can see them in this location, and then I brought out what I use to put the holes into the ductwork, which is a bad screwdriver and a hammer. And I will pound a hole into the ductwork, as you will see in the next slide. Now, you can use any type of drill bit to put a hole in there, but I have found that it is easier to use a screwdriver and a hammer to give me the hole that I'm going to use my aviation snips to go around the hole and cut it perfectly to fit in that damper that we have placed on it. So as we are looking here, I've drawn my holes using the takeoff as my template, and I'm taking my screwdriver at an angle, and I'm going to slice holes into the ductwork so that I'm capable of moving the aviation snips, or the left or right angled aviation snips, through the slit and then around the actual hole that I've drawn for the takeoff with the dampers inside of them. Hammer and a screwdriver, that's all you need. Now, you can use a step bit. A step bit, 3/4 inch step bit would work just as well for putting a hole into the ductwork, so we can slide our aviation snips in there. But your preference is whatever it's going to be when you get into the field. You'll see a lot of old timers using screwdrivers and hammers because it's right there, very quick to get it in there. Plus, we don't leave any little metal shavings on the inside of our ductwork as well. Okay, we got that hole in our ductwork, and now we're going to insert our aviation snips into the ductwork. And hopefully you have time to work with these aviation snips, but we're just going to work our way around that circle all the way until it's, we want to try to cut right on the line for that, because that's where those tabs are going to bend over and catch that ductwork and hold that takeoff in place, so that we are capable of moving air into the branch ductwork itself. So we'll take that aviation snip and we'll go around the ductwork hole there, and then we'll insert that takeoff into it, as we're going to see within our next picture. I've cut both holes out in the ductwork, and you can see that I am going to insert this takeoff into that hole. Now, after I've inserted the takeoff into the hole that I have cut, those tabs that you see on that takeoff, I am going to bend them against the metal on the ductwork, and that's going to hold that takeoff in place. You might want to put some screws in there as well, although you need to be careful that you don't screw one of the sheet metal screws into your fingers, because getting those tabs over and a screw in them is going to be very difficult, as flimsy as they are. But you should end up with a nice tight connection on that system on it. Sometimes I will even use a hammer to hammer those those tabs into place so that I got a nice tight connection on it that's not going to move around. It doesn't matter after I put the mastic on it anyway, and that mastic sets up. It is a tight seal once that happens, but this is the way that you install a damper with a takeoff with a damper inside of a branch ductwork, inside of a main trunk as we're going down through the system. Okay, now it's time for us to put the mastic on this fitting. As I'm going to show you in the next picture, I've painted the entire thing, but any gap that you see within this ductwork is a place for air to come out. So I will paint the entire perimeter of this ductwork. I will paint up this seam right here. I will paint the seam that's on the square ductwork or the main trunk as it's coming off. But I want to be careful that I don't put that mastic on that damper. That's going to inhibit that damper from moving from a parallel to a perpendicular form so that we can get that airflow through there freely. Later on, I'm going to show you what we're going to do with that damper, because once we have adjusted the airflow to the appropriate airflow that's going into that room, we will take a screw and we will screw that damper in place, and that damper will never move from the location that we have placed it in there, providing for us the proper airflow and CFM into our branch runs for particular rooms that are out there. Okay, so I painted that mastic onto that piece of ductwork, and you can see that I have done the seams of that ductwork on the square. I have done my takeoff, and I have gooped it on. I mean, I really want this ductwork to be sealed. Remember that 30% of your energy is actually going to be lost to air moving out of your ductwork. And we want to try to keep that air within the ductwork. And that's why that's why they say that mini splits are so much more efficient than a split system, is because the installers have failed in their installation process of putting mastic or duct seal on the ductwork that's in the attic or in the crawl space or in the conditioned space. We want to seal it. We want to make it nice and tight so that we can have the proper velocity pressure, total pressure, and static pressure within our ductwork. And we don't have to worry about lost conditioned air that we have failed to seal the ductwork up. So seal that ductwork up. Don't use tape. Use the mastic. I know it looks like crap, especially when you're dealing with open ductwork that doesn't have any insulation on it. This stuff, we're insulating it. It doesn't matter what the mastic looks like on the bottom side of it. We're going to cover it up with some nice foil back fiberglass insulation. So when we're looking at metal pipe that's running from the main trunk out of the takeoff and then going to the area in which we're going to be attaching it to a boot and then to a register to go into a room, those sections of pipe happen to be from 2 feet wide, 2 feet long to 5 feet in length. The sections are put together by putting 3 to 4 screws within the ductwork, and there are specific positions that you want to put those screws. So our round pipe that's sitting here will be put together through this Pittsburgh that's sitting on it. We can see it inserted towards the back end side. But what ends up happening is this pipe here is inserted into this section right here. And you have to bend the pipe almost oval in shape to get these Pittsburghs to lock in place along it, which is going to create a semi-airtight seal along this path that's right in here. Now, the screws that we're going to put into this ductwork, I say 3 to 4. So you're going to put a screw there, you're going to put a screw there, and you're going to put a screw in there. And this is going to hold that metal pipe or that round pipe from moving in any direction that we have on that particular branch. Okay, so we're going to put that together in that Pittsburgh. We almost have to take it and make it into an oval shape for that pipe to slip into the Pittsburgh of the metal pipe um, as we're running it. So sold in 2 foot sections, 5 foot sections from the supply house. Round duck usually used on branch runs. Very little restriction for the airflow as we're going through this compared to our flexible duct and the ridges that are on the flexible duct. Just remember that the screw patterns are here on the side and on the other side, and that's going to give rigidity to the piping so it doesn't move. And we want to do that on all the sections of piping that we put on there. Now, if we were to ever take that piping apart and to place it back together, we would want to take that piping and put some new screw holes within that piping on that system itself. Just one more thing in particular that we need to understand about our metal pipe as we're running. Our takeoffs are going to have our crimped ends, and we're going to want to continue that crimp in the direction of the airflow that's flowing. So the airflow is going to be flowing down this direction within our pipe, so our crimped end is going to be in that area. So as the air is coming down, that it doesn't find an easy way to flow out of the ductwork itself because we have installed it in the incorrect position, that it's just going to flow through and then create that static pressure that we want, the velocity pressure that we want, and the total pressure within the duct system that we want for it. And then we'll take these seams that are on this round pipe and we will mastic those seams with those screw holes that are sitting there so that we are able to provide a good airtight ductwork so we're not wasting any money by taking that conditioned air and moving it out. So a couple of different connectors that we'll see. We've been through the takeoffs. We've been through the metal piping that's on our systems as we're running. We've been through the dampers. We've been through the plenums and the main trunks, the square duct that we see, and then coming off the square ducts. If we need to make any turns or adjustments on that, what we have here is a round elbow that's adjustable for us to a 45-degree angle, to a straight angle, into a 90 angle, so that we can make the turns possible within our ductwork on our rigid metal piping. The same principle goes into the securing of these pipes as the round pipes are. We want to put 3 screw holes in there, put one there in our sheet metal, and put one on top. And then we want to mastic every portion of the air that's coming through there. So any place that where air can come out. And these joints right here are pretty notorious for moving air out of them. So we'll take our mastic after we have put this pipe in place, and we will seal up every aspect of that pipe. If we were insulating it, we would wrap it in our foil back insulation with our fiberglass to give us even more R value for our metal pipe itself. Just remember that we have our 3 screw holes to keep them in place. We can take this 90-degree angle and adjust it in any way, shape, or form. And that has to do with these places that we're going to seam right here, these seams. We can move this ductwork like we want to. We can take that direction, this one this direction, and this one that direction, and then opposite. Any way that we want to move this elbow, we can do that with the design that we have on it to make sure that we have the correct positions. Remember your 3 screw holes. Remember your mastic that you're going to be using to seal this duct up. And then we're going to be running this over, hopefully, to a boot, a register boot that's going to be placed in the floor for us to put that air into the vicinity that needs to be heated or needs to be cooled. Okay, continuing our process here of running that air into the room. What we're going to be doing is we have a termination that's going to fit into that room that's going to enable us to put some form of decorative piece, which we call a register or a grill, on that system. So what we have before us are what we call register boots or torpedo boots. And these are 4 by 10 or 4 by 14 or 4 by 12 different boots. Now, what we're going to do with our round pipe is we are going to take that round pipe and we are going to attach that round pipe to our boot, and that boot is going to stick up into the actual room that we are going to be conditioning. So we've taken it from the furnace or the air handler all the way to the trunk, the main trunks running out to our branch ducts with our dampers into this section of pipe right here. Now there are a couple of different sizes of boots that are out there. And I'm just going to write them down on the PowerPoint right here. And you go ahead and write them down because as you're doing your ductwork project, you're going to want to put these particular boots into the rooms the type of based off the type of round pipe that's running into them. Now, 4 by 12 by 7, that's the normal pipe size for a 4 by 12 register. And what we're dealing with is here's our section on our ductwork that's 4 inches. Okay, we'll cut a hole in the floor that's 4 inches, and then we'll come clear across. And depending on the type of round pipe that's going into our ductwork, let's say it's a 7-inch round pipe coming in, okay, we're going to be putting in a 4 by 12 piece of ductwork or register boot that's in there. There are many shapes and sizes to our register boots, and you will find that out as you are studying it, but also as you are putting this stuff in within the field. That our sections are 4 by 12, you're going to have a 7-inch pipe. 4 by 10, you're going to have a 6-inch pipe running into it. And a 4 by 14, you're going to have an 8-inch pipe running into that. And that's all about air volume or CFM volume coming out of that register for it. But these are your 3 common sizes that you're going to be seeing for your ductwork. They do make other sizes that are out there, but this is a register boot that's going to be fitting in there. Now, these joists that are running, what will end up happening is on the basement or in the attic, we'll have these joists running. We'll have our 7-inch pipe that's running through our joists. And then if we get really, really, really close to our joists, we want to use a torpedo boot because that torpedo boot will hug the side of our joists. If we're right in the center, we're going to use a regular boot right here. This is a 90-degree boot. They make straight boots, but just come to understand that I'm not asking you for particular types of boots that are out there, but when you were looking at these, that these are the boots that are going to be fitting up within the conditioned space of the building, and it's going to blow the air into that conditioned space out through the register boot that's sitting there. So continuing on our process, we have different types of fittings that are going to fit on our rectangular pipe or rectangular flow on our systems. And also this is going to be test questions and homework questions that you're going to want to go through this PowerPoint again and kind of name off different types of pipes that are out there. Now, this 90-degree elbow here that we're looking at, if you were to lay it flat on the ground, you would notice that it is in a horizontal aspect. So the 90-degree is going in a horizontal direction, and it is not going in a vertical direction like the other pipe is. So this pipe right here that would fit on a square duct coming in sections that are 8 by 16, 8 by 18, 8 by 20 will be a horizontal application. Okay, so our 90-degree is horizontal. Over on this side of the pipe or on this side of the PowerPoint, we're looking at a different type of 90-degree ductwork, and this one is in the vertical location. So as my trunk is coming along on the horizontal, it would horizontally turn to a 90-degree angle. If I was dealing with a vertical, my piping would come along and would go vertically up. So understand the difference that you're seeing on these. And this one that you can't see because my face is right in the front of it, it's a vertical 90 that we're looking at on that particular system. Also on the left hand side is a horizontal 90. And you can tell by the difference in these. Understand them. And then as you come up to your homework, name them correctly as we're going through that process. Now, sometimes you might run into a situation where it's kind of hard to fit two pipes together, especially when it comes to the metal piping. Getting into tight locations, we might want to use something called a drawband round pipe connector. This has a worm gear that's on it. We would fit this around our round pipe where there's a gap because it's hard for us to fit the boot assembly. If you're doing this correctly, you'll never have to use one of these guys ever within our systems, but you might have to in some cases where the pipe is hard to bend into the position that it is, or somebody went in, they nailed the boot in there, and it's going to be impossible for you to get that boot off that you could stick it up within the piping itself. We can use a drawband pipe connector on our systems, and you should be good to go with air tightness. And also with this, we're going to mastic it up. Put that caulk on a brush around this as well to create that airtight seal for our ductwork in itself. So as we're coming along, we're running that ductwork or that main trunk right down the center of the house. Hopefully, you got your furnace. Okay, off of that, you got your plenum, maybe your A coil sitting on top of your furnace right in here. We got our plenum coming up, and then we're going to run our trunk this direction. At the end of our trunk, what we're going to have to do is we're going to put an end cap, and that's what we're seeing in the picture right here. Is an end cap that's going to stop that airflow from going any further. What this is going to do for us is going to back that airflow up, create that static pressure, create that total pressure that we need within the system to push that air out. The different types of trunks that are running along this entire uh, system. So branch trunks would run off of there over into a boot type system. And don't forget about our dampers that are in that trunk as well. So this end cap is going to create that pressure that's going to force that air up, down, forward, and then also backwards as we create that pressure. So air pressure in all different directions. And as it builds back, it's going to force that air evenly throughout all the branch runs that are in this particular system itself. Now, this is just an example of the end of the trunk, as we can see, running all the way down through the center. Right down there is our furnace. We can see our furnace right in this area here. In this location right here, I'm going to blank this off with a piece of metal that I'm going to call an end cap. It's going to stop that airflow and build all that pressure that's on that system. Now, sometimes when you're dealing with different municipalities, different locations, different codes, it may be required for us to bring in fresh air uh, for um, for that living environment or that office space. What we're going to do is duct it to the outside, and we're going to bring in a fresh air trunk into the actual return piping of the system. And as the return piping, as the furnace turns on or the air handler turns on, it's going to take that air, suck it in from the outside. It's going to suck it into the building. A couple of things that this is going to do for us is it's going to create a positive pressure on the inside, and it's going to minimize our um, our infiltration and our ventilation CFMs that we are going to need for that environment itself. Different types of systems will have some sort of mechanical ventilation, and this is what we're going to be doing here within this system is giving us mechanical ventilation rather than having that air infiltrate through the windows, infiltrate through cracks in the wall. It enables us to actually condition that air before it actually enters the space, the conditioned space, so that we can so that we can control the amount of infiltration that's coming into that building by bringing that fresh air in. Otherwise, we have no control over it. It comes in as it pleases through cracks in the wall as air escapes out. And this just gives us another way to control the environment that our customer is in to make it more comfortable for them, especially when it comes to humidity and temperature control. Well, some of the different types of connectors that you will find on your systems. We talked about the S-Lock. Well, this is a lot like the S-Lock. This is called a standing seam S-Lock. You take that S-Lock where the two pieces of metal are going to fit in between it, and we add a seam to that S-Lock. And what this is going to do for us, it's going to add rigidity to the ductwork itself. It's going to add strength. I like using this standing seam when I'm trying to hang piping or ductwork. Just gives it something to go across that gives it a little bit more strength than what that original S-Lock would give us. Another term that we use for this is rigid S-Lock or standing seam S-Lock itself. Okay. So, in order for us to cut down on the amount of heat loss that this metal pipe is going to create for us, we're going to use fiberglass insulation that we're going to wrap around that particular ductwork that has been sealed on the inside, and it's going to create for us a vapor barrier for one. And the second thing it's going to do for us is create a layer of insulation that's going to resist the flow of heat through that ductwork into the environment. Remember, heat will want to flow from something that is hot to something that is less hot. So if we can slow down that process by putting some sort of insulation on that ductwork, then we will have kept the conditioned air from absorbing heat. And if we're actually throwing heat into the environment, the heat that we have put into the air will keep it from escaping the ductwork, so that we can save as much money as we can on that. Now, this particular fiberglass insulation can be installed on the exterior of the pipe, or it can be installed on the interior of the pipe. My preference, and this is my preference, let me say that again. My preference is that you put the insulation on the outside of the pipe, so that we do not restrict the flow of air going on the inside of the pipe. If we were to put the insulation on the inside of the pipe, then we would have to make the ductwork bigger to handle the airflow that's coming through it. That's why I always like to run exterior insulation rather than interior insulation. The exterior insulation, as I will talk about, and as you will see in the next couple of slides, has to be wrapped on the pipe, not too loose or it looks really bad, not too tight or you lose the R value of that pipe, but just the right amount of tightness so that it fits around the ductwork, and anywhere that there is a really tight connection on this insulation to the metal, you're going to get more heat transfer in that way because you're smashing that fiberglass insulation down from being 1 inch to maybe being 1/8 of an inch on that particular duct. When we're speaking about the insulation that goes on the interior of the pipe, if you ever have to do it, we're going to use stuff that we call tabs, and these tabs are going to have uh, little metal clips on them that it looks like a nail that's glued to the side of the interior of the pipe, and we put the insulation over top of it, and it is a special insulation that goes on it that does not flake off or put particles into the air. Um, that's going to be breathed in by the customer. And that'd be the only reason that I would not prefer interior insulation on your ductwork, because over time, this stuff is going to break down, and I don't like the idea that we have that type of insulation in the airstream that individuals are going to be breathing. So I prefer it on the outlet, on the exterior of the ductwork itself. So tabs will be glued to the inside of the ductwork. We'll glue the inside of the ductwork, and before we bend up any type of ductwork, we'll lay a piece of insulation across it, and then we'll bend up the ductwork so that the insulation's nice and tight on the inside. Another reason to put exterior insulation on your ductwork is, well, the glue and the tabs can fall off on the inside of the ductwork and cause an air restriction on the inside of the ductwork. Hard to see because it's interior, but only diagnosed because you have bad pressures on your low side system or your furnaces kicking off on high temperature within that system itself. Usually applied in the shop as they're making that ductwork up. Okay, here's a great example. We're gonna measure this ductwork. Okay, and what I always do is I add about 4 inches extra after I've measured all 4 sides of the ductwork itself for that insulation that's going to be going around the exterior of the ductwork. I'm going to fold it up into a little seam on that ductwork, and I'm going to use my stapler. This is a special stapler for that ductwork, and I'm going to go around the seam of that ductwork, making it nice and tight, but not too tight. And then I'm going to staple that seam of that ductwork all the way down through that system so that everything's nice and tight. A lot of people, they'll just use tape on this fiberglass insulation. That is the wrong way to install fiberglass insulation. Fiberglass insulation needs to be stapled, and after you're done stapling it, that is when you tape it. Now, this is a foil back insulation, which you'll be using out in the field. This is a vapor barrier insulation that's going to keep the moisture from entering into the insulation and getting close to that ductwork and then sweating on that ductwork. So it's very important that if you get any scrapes, any gashes, any holes within that foil, that you are using the foil tape that comes with this ductwork insulation to put on that hole to maintain the vapor barrier of that ductwork itself. So I'm going to take that seam, going to staple it all the way down that insulation. After I get done installing or stapling that entire seam, I am going to fold that seam over the ductwork, and I'm going to use foil back tape. There are many different types out there. You have to see what your manufacturer wants you to use. And I'm going to fold it, put that tape on the seam all the way down that particular insulation. I'm going to use a special tool called a blaster or a squeegee or whatever device that they'll call it in the field. But that blaster is what we're referring to it as, is going to be sitting right there. And all it is a flat piece of plastic that I'm going to take and I'm going to rub it over the tape that I've just placed down onto that insulation. And that's going to give me a nice tight seal for the foil back insulation that's going to prevent the vapor from entering into the insulation itself and into the ductwork itself. Remember, tape it, fold that flap over after you get done stapling it, and then tape it on there. Now, as you can see, I have placed that ductwork in the vicinity as I'm running it over. You guys can see it right here in the corner of it. I have placed a boot, a straight boot, going straight down into the environment that I wish to put the airflow in them. I'm going to use a horizontal 90, and I'm going to come across and go this direction, and I'm going to use flex duct that I'm going to attach to my takeoffs that I've ran here, and I'm going to run it above the ductwork and then into that, and then continue this ductwork out to the right beyond the picture that you guys are seeing right here. You can see the foil insulation that I put around the ductwork, nice and tight, not too loose, not too tight. You can see the gaps that I've left in here, and you're going to have these gaps in there. I'm going to come back through, and I'm going to run foil back insulation underneath that ductwork, and I'm going to put mastic and seal up that ductwork that's on that ductwork right there. Mastic it up so I got a nice tight airtight connection, and then I'm going to put insulation, foil back insulation in there. Do the same process that I just showed you previous. Staple the seam and then tape all the seams up with the foil back insulation that's on there. And you're going to be working in some really tight environments when it comes to installation of your ductwork. Just where make sure that I hit my head on these nails in this roof many times and put big gashes in my head. And it's not a fun job to install ductwork, but it's something that's necessary when we're installing AC into a house. Flex duct is an easy, fast way to install our airflow. The only problem with flex duct is there is a limit to how far you can run flex duct. Okay, so that limit is 15 feet for residential. Residential applications is 15 feet. A lot of commercial applications, you are going to be running no more than 5 feet of flexible duct. And they do this for a purpose, and that purpose is that the flex duct restricts airflow quite a bit because of the ridges on the inside. Now, the benefit of flex duct is it's fast and it's easy. The second thing is I don't have to insulate it. It's already insulated. So I don't have to run some sock over some metal pipe for my branch runs that are running out there. The insulation is already on there. Easy to hook up, easy to install. Just got to make sure that we're stretched properly so we're getting the proper amount of airflow through that system. When you look at flex duct installation, the boxes are going to come in 25-foot lengths. Okay, but that does not mean that you can run these boxes 25 feet. I've seen a lot of bad installers, and they'll run 75 feet of flexible duct. That's not a good idea. There's a lot of air restriction when it comes to these flexible pipes because of the rigid wire that they have ran through that particular pipe. So, not good. We're starting to get rid of the vinyl outer coating that's on our flex duct and starting to go with all foil back insulation that's on there. And I would have to say I prefer the foil back because it's easier for me to take my insulation that's around my rectangular duct and transition it into the foil jacketed flexible liner that's out there. So how do you cut it? How do you attach it? We're going to cut it with a duck knife. And that duck knife is going to have a tool that's on it that enables me to cut the wire that's on the inside of the duck. This stuff is extremely easy to cut, extremely easy to work with. In the book and on your test questions, it's going to ask you, how do you support this? It needs to be supported every 4 feet, and it needs to be supported with an 1.5 inch strap that's on that ductwork. So there's your answers to your questions for your homework. 1.5 inches strap, but also it's going to be supported every 4 feet. Maximum length, residential, 15 feet, no more. Get that round pipe as close as you can to that boot. And then if you need to, run your flexible duct to the actual boot. And then no more than 15 feet for residential. Commercial applications, a lot of them are gonna scale you back and tell you no more than 5 feet for the commercial applications that are out there. So this is what it looks like when we get to the point where we're taking this from the trunk on our systems and then going to be running it into the boots that are on our systems. We'll take that foil and we'll take that insulation and we'll peel it back and we'll expose the vinyl inside that has that wire that's rigid. And that wire, you can see that wire right there around our particular pipe that's on there. So that wire is what's going to give that vinyl its rigidity, that's going to keep it stretched tight so it doesn't collapse in on itself. And then what we're going to do is we're going to stretch it over top of our takeoff. Remember, our takeoff was put into the square pipe and it has a damper on it. We're going to stretch this guy over top of that takeoff, and we're going to use draw bands, big wire ties that we're going to take and tighten with a special tool. Do not use your fingers to tighten this. You cannot get it tight enough. You have to use the special strapping tool that goes around this and tightens it. And it tightens it so well that it's actually going to cut it when it's at the proper tension for that particular flex duct. Now after that, I use duct tape at this point, and I'm going to duct tape that vinyl against the metal with my mastic around the gaps of the metal to metal application that's there. Now after that, I'm going to roll that insulation over top of that takeoff, and then hopefully we're going to have some insulation sitting on this metal pipe, and I'm going to tape this foil back insulation that's on my flex duct to the foil back insulation that's on my rectangular pipe right here. Give me a nice, tight, vapor seal insulated pipe running to my different distribution boots into my areas for that system itself. So another type of insulation ductwork that's out there for us to install, it's called ductboard. I am not a big fan of ductboard, but it does save time in insulating. It does save time in actually installation of the unit itself. So what is it made of? It's actually made of insulation that's pressed together, fiberglass board with a reinforced vapor barrier foil back on the ductwork itself. It is lighter than metal. It helps cut down on the transmission of noise because of the dampening of the insulation that the ductboard's made of. We're going to secure it. We're going to cut it to a certain style. We can make transitions, takeoffs, all sorts of things we can do with ductboard. It is very itchy. We do secure them in place by using a special staple that curves outward. So if I was to draw that staple for you, it comes down and curves outward like this. It comes down and curves outward like that. So that staple is what's going to hold that ductboard together. We create flaps and grooves that the ductboard will fit inside of the other ductboard, and that flap is going to be taped over top of the other ductboard that's running in this direction, giving it a nice tight air seal, so no need for any mastic or caulk on a brush to seal the air that's coming out of these units. Has to be well supported because it's not as rigid as our metal ductwork. So looking about every 4 feet, supporting this ductwork with some sort of strapping or unistrut to hold up that ductboard on it. Like I said, I am not a big fan of ductboard, but to each his own. A lot of installers will prefer ductboard. I prefer not to run it for personal reasons. We'll just say that. So as we're talking about the ductboard on our systems, this is an example of what that ductboard is going to look like, preventing the vapor from getting into the system, the moisture. By that foil back insulation that's on there, we can see these are pressed together. We can see that we can cut grooves into this ductwork, and I'll show you that here in a little bit. That we can take this flat piece of ductboard, cut these grooves into that ductboard, and then create our square um, airflow ductwork out of it. And no need to insulate it because the ductboard is already insulated. Make sure that you're wearing your goggles and your gloves and a long shirt while working with this. This stuff gets really, really itchy, and it's put together and taped together for a good seal. Supported very, very well. So what we're going to be looking at as far as model number explanation for different systems that you will see within the field. Now, this is a particular model number for a particular brand of furnace. I think it happens to be a Rheem or a Ruud type of furnace. And the nomenclature on it has different meanings for us, for the manufacturer that's producing that piece of equipment. Now, what I'm trying to look at here is this will tell me whether the unit is, it'll tell me the voltage rating on the unit. It'll tell me the controls, how we're controlling this specific piece of equipment, the series of which it is, the metering device that's on it, the coil efficiency on the unit, the width of the unit itself, the nominal capacity, which is what I'm really, really concerned about, is that nominal capacity on that particular unit. Motor types, types of airflow, stages of the unit, whether it's a two-stage unit or a modulating type of unit, and then product category of this piece of equipment that we're looking at here. Now, this just happens to be an air handler instead of an outdoor unit. We can see that one of the more important things that I want to look at on this air handler is the nominal capacity of that air handler. I want you to notice that they're going to come in in stages from 12, 18, 24, 30, 36, 42, 48, and 60,000 BTUs when it has to do with residential applications. So the 24 on this number is what I'm really, really concerned about on this piece of equipment, because that's going to tell me the tonnage of the unit, and that I will match the tonnage of this unit with the tonnage of another unit out there that's an outdoor unit, and then I will pipe that unit into the air handler, which we're looking at the air handler itself, the model number explanation of a Rheem type air handler as it's out there. So we look at the brand, it will tell us the brand, and they'll put that on there when we are buying the piece of equipment. We know that the product category is an H. We see that right here. It's an H that tells us an air handler. It's a 2. And if I come down to the stages of airflow, it tells me that there are 2 stages of airflow for this particular unit. The T has to do with the motor type, which is an ECM type of motor, constant torque, and not a variable speed ECM. The nominal capacity happens to be a 2-ton, 17-inch cabinet with a EEV, or an electronic expansion vice on there. And we're going to gain all that information from that model number itself. So it's very important to look at it. Now, if I was to ask you what the voltage rating of this would be, I would come out, and this one particular is a J. Come down to the J, and we can see that this actual unit must be a European unit because it's 208, 240, single phase, 50 hertz for that particular unit there. But that is how the actual model number will break down on the system itself. Now, as we continue to look at this system, let's go ahead and highlight what I'm really concerned about is the nominal capacity. So we see 24. Now, if you don't have the breakdown of the actual unit, well, just look for multiples of 12. Well, 12, 18, I know 18 is not a multiple of 12, but 12, 18, 24, you're going to see these numbers sitting inside of the actual model number itself. So we can kind of pick at it and see what the capacity of the unit is without actually looking up the breakdown of how the actual manufacturer is giving the capacity of that actual unit when we look at it. Now we're going to swing across and look at a couple of different units that are out there. What do you think here? Unit model number explanation. We're looking at an RA14 24A J1NA. And just by looking at this, I can see a multiple of 12 right there. What happens to be the 24, and that 24 is going to tell me the capacity of that particular unit there. And we see it as a 24,000 BTU capacity for the unit as we're looking at here. And this just happens to be, I do believe, um, a a condensing unit that we're looking at. R tells you the brand, it's a Rheem. Heat pump, A. 14 tells you the SEER rating of it. 24 tells you the BTU capacity, and then the major series in A. We look at the voltage of this one, and we're dealing with 208, 230, 60 hertz. So it must be an American air handler that they're putting out. And then type 1 single stage.
So I'm
N,
not
which
quite
is
sure what happened
non-communicating
to
system,
uh,
and A
the
is the
video
minor
on this
series of
particular
that particular.
slide, but we'll go ahead and look at this. And I think we were talking about model numbers and serial numbers on units, and specifically the tonnage of those units as we're looking at them. This particular unit model number has a 24 in it. So that's telling us that this unit is a 2.5 ton. Once again, we have the model breakdown for the model nomenclature plate, breaking down an actual unit and looking at it. These are model numbers of an outdoor unit, and the model number is going to break down and tell you what the voltage is, what the refrigerant is, what type of unit it is, air conditioning or a heat pump. Is it a variable speed, split speed, light commercial unit? All these different things we're going to be looking at, and what SEER rating on it as well. The one thing that I really want to pay close attention to on the model numbers is the tonnage of the actual unit. And that's why it's important for us to look at these units and to distinguish between um, different tonnages of units that are out there quickly by looking at these numbers. So we're looking for multiples of 12. And if we were to look at this particular one, we're looking right in this, and that's 7 or 8 on these systems. And we're looking at 4TWV0036. The 36 tells me that this is a 3-ton unit. We can verify that by following this line down and coming down here. And we see that the nominal capacity for this unit, it's rated in thousands of BTUs. So we got a 36,000 BTU. So 36,000 BTU air conditioner. And if we were to divide that by 12, which 12,000 BTUs is 1 ton of air conditioning per hour. We'll divide that by 12, and we'll end up with a 3-ton air conditioning unit. We're going to divide it by 12,000 BTUs. So divide that by 12, and you'll end up with a 3-ton air conditioner on this particular unit.
So we'll continue to look at our nomenclature plates or our tags on our outdoor units. This one is an Allegiance 13, manufactured in 2007. There's a couple of questions that I need to ask myself for this particular unit. What size minimum breaker can I put on it? What size minimum wire size can I put to that breaker? What size maximum breaker? So what we're doing here is we are combining both what you have learned in electrical and what you have learned in air conditioning, and we're putting them together so that when we go out and look at these particular units, that we will have an idea about what breaker size that we have to put on this unit based on the nameplate of that unit. And going back to the NEC, the National Electric Code, we'll be able to tell what type of wire size that we have to put in for this unit based off the minimum amperages and the maximum amperages of this particular system. Okay, so walking down through this model number, the first thing we're going to indicate right here in the red, that's our voltage. Okay, number of phases, we are dealing with single phase, 60 hertz, minimum circuit conductor amperage. We're looking at 13 amps. So that's the minimum circuit amps that are going to be on this particular unit. We have a minimum breaker size that goes in this unit, and we also have a maximum breaker size that goes into this unit. This one happens to be Trane. American Standard is another Trane product that's out there, so they're just giving us different names. They slap these names on them, but they're produced by the same manufacturers out there. So, couple of questions for you. So, what size minimum breaker can I put on this unit? I'll give you a couple of seconds to think about it. We're looking at the nameplate. We come up here to the minimum fuse, minimum breaker, and we find out that this particular system, the minimum breaker that we can put on it is a 20 amp breaker. Now, taking your knowledge back to electrical, 14 gauge wire. Okay, 14 gauge wire can hold up to 15 amps. And guys, these are minimum. If I was to get a breakdown of the actual wire that was running to this particular unit, you would see that a 14 gauge wire can actually, under certain circumstances, take more than 15 amps. But NEC code requires that a minimum circuit breaker be put on these particular wires so that they do not exceed a certain amperage on them. And that is found in the NEC book. 14 gauge wires, 15 amps. No more. Can't put any more than 15 amps on that particular wire. If we do that, that wire has the potential to burn up. The next gauge of wire that we're going to be dealing with is a 12 gauge wire. 12 gauge wire is good for 20 amps. And we're just taking you back to your electrical knowledge in the field. And then for the next size up, we're dealing with a 10 gauge wire. And that 10 gauge wire is good for up to 30 amps. And these are the minimum breakers that you can place on the certain size wire going on this particular unit. So when I ask you, and the data plate tells us that the minimum breaker that can be installed on this system happens to be a 20 amp breaker. Well, what size wire do I have to run for a 20 amp breaker? I go back to the NEC, and the NEC says a 20 amp breaker, you have to run a 12 gauge wire. So the answers up here is the minimum circuit breaker is a 20 amp. Okay, and I have to run a 12 gauge wire. Okay, next question that we need to ask ourselves is what's the maximum breaker that I can install on this particular unit? And the maximum breaker that I can install on this particular unit happens to be, because of the nameplate that's at the top of it, a 20 amp breaker. Well, What is the minimum size wire that I can run for this particular outdoor unit? And it is a 12 gauge wire. Question number 2. Can I install a 10 gauge wire on this system? And the answer is yes, because the 10 gauge wire can take 30 amps, and I have a 20 amp breaker on this circuit that will protect that wire. Remember, the breakers are there to protect the wires so that we do not catch on fire. Okay, next question. What size tonnage is this unit? I'm going to check the model number. Got 2A7A 3030A. There's my model number. You guess, without looking at the breakdown of this particular unit, your guess is as good as mine, but we can make a good educated guess right here and know that we're probably dealing with a 2.5 ton. Now I'm going to be looking at these two numbers here. I don't know the breakdown of this particular model, but I know that I have two numbers that could actually be the tonnage of the unit. So 30 would equal out to be a 2.5 ton unit when I'm looking at the refrigeration that's on this particular unit itself. Okay, another breakdown of a nameplate that's on a unit. I got minimum circuit amperage or minimum circuit amps at 18.2. I got a maximum fuse on this one that happens to be 30 amps. So a couple of questions that I want to ask for you. My minimum amp draw is 18.2. What size wire can I use for this particular unit? What you will do is the minimum circuit amps is 8.2 on this one. So I should be able to use a a 12 gauge wire, which is good for 20 amps. The only thing I don't know here on this particular unit is the minimum amp draw for this unit is 18.2. There is a code in the NEC that I would take 18.2, I would multiply that by 1.25, okay, and I would end up getting a number that would be over 20 amps for this particular system. Now, if that was the way I was actually sizing the wire for this system, I would not use a 20 amp breaker for this particular system, and I would not put in a 12 gauge wire for this particular system. So 18.2 times 1.25, I end up with a continuous amp draw of 22.75, which is well over my 12 gauge wire. So I would not use a 12 gauge wire if the NEC code was followed on this particular unit, even though the minimum circuit amperage on this particular unit was 18.2. Um, Given the fact that we also are given a maximum size breaker on this, I tend, as a HVAC technician, to always go to the maximum amp draw of that particular unit and the maximum fuse for that particular unit, and then install the correct breaker and the correct wire for the maximum fuse or the maximum HVACR type of circuit breaker for that particular unit. So what size breaker, if I was to use a 20 amp, I would put in a 20 amp breaker or fuse for if I was going to run 18.2. But we've already talked about that, and we've already discussed that we're going to be pulling over 20 amps on that particular unit. Now, the maximum amps for this one is a 30 amp breaker. What size wire? Going back to our other slide, we can see the size wire that we want to use for this is a 10 gauge wire. That 10 gauge wire is good for 30 amps. I do not want to put a breaker in that's larger than 30 amps on this. One, the tag told me not to. The second thing is, if I ran a 10 gauge wire and I put a breaker in that was over 30 amps, then that wire has the capability of burning up. And the NEC, the National Electric Code, tells us that we cannot run a wire um, We cannot put a breaker in there that's larger than the wire current on there. Plus, we have minimum breaker sizes for the smaller gauge wires that we have, and that runs in a 10 gauge wire. You cannot put it above a 30 amp breaker on a 10 gauge wire. Okay, now we are moving on to another unit. This is an outdoor unit. It's a Ruud air conditioner. I can guess the tonnage. Got an O30 right there. So you guess it. I'll guess it. I think I have a 2.5 ton air conditioning system. So divide that number by 12. You'll end up with a 2.5 ton system for this particular unit. Now, what's going on here with this system? I have a minimum supply amperage amps going to this unit. I got a minimum circuit breaker that goes on this unit. And I also have a maximum circuit breaker that goes into this unit. The type of breaker that I want to use for this is an AHCR type breaker. So if I was to put the minimum size breaker in for this particular unit, what size wire would I need to run according to the NEC? Remember, 14 gauge wire is good for 15 amps, 12 gauge wire is good for 20 amps, 10 gauge wire is good for 30 amps. So if I put a 25 amp breaker, which is the minimum breaker I can install on this system, it's a common breaker in the field. What size wire can I use? Can I use a 12 gauge wire? The answer is no. NEC says nothing over 20 amps on a 12 gauge wire. Can I put a 14 gauge wire in there? Absolutely not. The 14 gauge wire is good for 15 amps. If I put a 25 amp breaker in there, I'm burning that wire up. It's not going to be able to handle the amps that particular unit's going to be running. NEC says a 10 gauge wire is good for 30 amps. Can I install a 25 amp breaker on a 10 gauge wire? And the answer to that question is yes, because the 25 amp breaker will trip and the 10 gauge wire is capable of handling up to 30 amps of electrical current going through it. So if I was going to use the minimum fuse or the minimum circuit breaker for this unit, I would put it at 25 amps and I would use a 10 gauge wire. Now, what would happen if I decided to put a maximum circuit breaker on this of a 30 amp? That particular unit, 30 amps, could I use a 12 gauge wire? Nope. I would stick with my 10 gauge wire on this unit, and that 10 gauge wire would handle up to 30 amps, and the 30 amp breaker would trip, protecting the wire that's on that particular unit itself. Going to go through and on there. So anyway, let's go on to the next slide and take a look. I have a unit that does not have a minimum or maximum breaker on this particular unit. So what do I do in this case where I have a motor that I'm trying to wire up on this particular unit? I would I would use the NEC, okay, and it gives you the unit and the corrective max amp draw for that unit. The nameplate above only gives you the amp draw on it. So what you're going to end up doing is you're going to take the amp draw of that unit and you're going to multiply it by 1.25. So where do we find the amp draw? Right there. So take the amp draw of that unit, 34.9, and you're going to take it and you're going to multiply it by 1.25. And you're going to end up with a breaker size, a maximum amp draw on this particular motor of 43.635 amps. Okay, let me back up here so that you guys can understand what's going on. This particular outdoor unit, motor, rooftop unit, it doesn't matter what it is. If it doesn't give me minimum and maximum breaker sizes to put on this particular unit, then I have to use the National Electric Code to come up with a particular amp draw on this unit based on a corrective factor given to us by the NEC, and that's 1.25. So 34 amps times 1.25, we end up with 43 amps of electrical current that I have to attest for this particular unit. So what size breaker am I going to use for that? I'm going to use a 45 amp breaker. Okay, 45 amp breaker is going to be used to protect the wire that is on this particular unit. Now, what I will do is I will go to the NEC, the National Electric Code, and I will see what type of wire I can install for this 45 amp breaker that we're going to install for this particular motor that's out there. So using the NEC, I'm going to go down through, I don't know what type of wire that I'm going to use, but I do not know the termination fittings that are on that particular wire. Some of these are 60 degrees Celsius. This one's 75 degrees Celsius. And this one is 90 degrees Celsius. If I do not know the termination temperature at which the unit is going to be running, then I always have to use the lower or the cooler number for those wires. So even if I come over here and I decide that I'm using a THWN wire that's good for outdoor use, I cannot base the amp draw off of this particular column because I don't know the termination degrees that wire is going to be landed on. So we will use the first column. A good rule of thumb is always use that first column when you're doing your amp draws so that you don't mess up and put a wire size in that's going to be too small for this. Okay, so going back to that, we're going to be looking at this first column. Okay, can I put in a 40 amp wire on 8 gauge? And the answer to that is no. I have a 45 amp breaker in here. The 8 gauge wire can only handle 40 amps at 60 degrees Celsius. So I can't use an 8 gauge wire. So I will step it up to the next wire. I will find out that the 6 gauge wire can take up to 55 amps. Can I use a 6 gauge wire with a 45 amp breaker? And the answer to that question is absolutely yes. So I want to choose the 6 gauge wire at 55 amps. Will the breaker trip before it hits 55 amps? Yes. So the breaker will protect the wire from burning up. And we base that off of our NEC constant running amperage of 43 amps. I'm going to put a 45 amp breaker in there. Go to the NEC amp chart to find out what type of wire I need to install. And I end up installing a 6 gauge wire. I hope you understood that. If not, send me an email. If not, ask me questions in the classroom. I will walk you down this particular process. But for the most case, most of our air conditioning systems that are out there will give us minimum, maximum breakers and amperages that we can use on those particular units. And then we will know what size wire and what size breaker to
So
install
your
based off that. If we don't,
high voltage electrical,
this is the
uh,
process that we have to
typically
use.
going to be installed by an electrician. They're going to bring it out to the outdoor unit on a new install, and then we're going to take that system power, and then we're going to hook it up from the disconnect into the unit itself. The control wiring is usually ran by the field technician. The field technician is going to take that wire and run it from the indoor unit to the thermostat, and then from the thermostat's going to tell the outdoor unit to what it needs to do. All the wires should run into the indoor unit and be distributed out. We're talking about our thermostat wire or a control wire needs to be brought into the indoor unit and then distributed out to different components that we want to run. Those components that we want to run are the thermostat and the outdoor unit. So whether it's an air handler or a furnace, all of our connections are going to be made in the indoor unit itself. So in particular, we're going to be using the NEC to run our electric into our pieces of equipment. NEC is going to dictate wire size, running wires. Workmanship has to be brought to a minimum standard when we're running these electric uh, wires. And then installation standards, enclosures and disconnects, whether they're weatherproof or the wiring that we're going to be running into a wet location, all going to be dictated by that NEC. Now, what I'm showing you here is a picture of a liquid tight connector. These are the conduits that we're going to be running on the outside of the unit. It's going to provide a protection from the weather, UV protection, but also wet weather applications when we get into that later on. But these are liquid tight connectors, and they're specifically made to attach outside to that whip and disconnect as we're running it from the disconnect to the outdoor unit itself. Another thing that we'll be doing as field technicians is running those wires into cavities where the walls already have drywall on them to place our thermostats in the correct location. And we'll use an electric snake to run those wires into the hole and then run that wire back down into the unit that's sitting on the outside of the to the indoor unit and then out to the outdoor unit. But if we have the wall cavity with the drywall already on it, we're going to use that fish tape to run that particular wire up into that wall. So we're continuing our conversation on the electrical hookup of the outdoor unit, the indoor unit. What we're discussing and what we're looking at here is when you bring in power to the outdoor unit, you're going to do so through a type of liquid tight connector because the condensing unit is sitting on the outside of the house. And then after I've brought it into the electrical compartment of the air conditioner, I'm going to land that electrical right on the contactor on this L1 and L2 terminal. Now, these should be labeled on the contactor, L1 on this side, L2 on this side, or something very similar. I could have flip-flopped the L1 and the L2 on there if I needed to. And then on the top up here would be a T1 and then a T2 on the other side. Now, I'm going to bring the line voltage into the line side of the contactor. The line side of the contactor may have a couple of wires hooked onto it, depending on what the schematic drawing is trying to tell us. But for the most part, I'm going to have these two wires here. Now, they're probably going to be color coded out in the field. We'll use black and white, but for the most part, the NEC is our standard for this. So we'll be doing black on one side of the unit, and then the other color for this side will be a red color, and that's just indicating that it is a 240 circuit. But it really doesn't matter the colors because we're just bringing in two hot legs into the outdoor unit. And make sure that you check your nomenclature plate to find out what your voltage actually should be for that unit before hooking it up. Remember, furnaces are 120. Outdoor units are typically 240 volt systems. Electric furnaces, air handlers are 240 volt as well. Now, when we get into tolerances of voltages on our units, we're looking at what is the nameplate voltage reading for this unit. And based off of that, we have a 10% variance on that unit that is acceptable for that unit to start up. So for a system that is single phase, 208, 230 system, the acceptable range for that system happens to be 187 volts to 253 volts. Don't want it to drop below that. So we're going to be watching this electric as we are kicking on that unit to see what the drawdown of our actual system is for that. But our compressor will operate at 187 volts. And then if we get too high of a voltage on this particular unit, the tolerance for that is 253 volts. So we have a tolerance of 10% either way on that system when we look at it. Our actual wiring that we're going to be doing for this particular unit is going to be our high voltage. For our high voltage, what we're going to be doing is coming into a main breaker box. That main breaker box is going to be fed by a 240 or 120 circuit, depending on what the nomenclature plate is for the indoor unit and the nomenclature plate is for the outdoor unit. We'll be running a 240 circuit to the outdoor unit disconnect. And remember, the disconnect always needs to be within reach of the outdoor unit so we can quickly shut it off, or within 5 feet of that outdoor unit so we can turn it off quickly or do something that we need to do as we are servicing that unit. Power supply will then be ran from the breaker box into the indoor unit, which is sitting over in this location here. Here's our outdoor unit, here's our indoor unit, and then here's our main breaker panel for the wires that we are going to be running on that particular unit itself. So understand that along with running this, we'll size the breaker for the outdoor unit. We'll size the wire size to handle the voltage and the amperage for that unit itself. We will install a disconnect for the high voltage to quickly shut off the power, both on the indoor unit and the outdoor unit. And then we'll hook up those wires to the appropriate locations within the indoor and outdoor unit, giving it its high voltage power. This next picture that we're going to be showing you happens to be where we need to put the service disconnect for our particular units. The service disconnect is what we're going to be using to shut the power on and off to the outdoor unit. Now, this can be a straight switch, or it can be an actual breaker that we're going to be using. For the most part, if it's we can have both. We can have a breaker, we can have fuses, we can have just a normal square D switch, but it has to be within reach of the outdoor unit or within 5 feet of the outdoor unit so we can quickly shut off the unit for servicing this unit on the system itself. This is an example of a disconnect switch that we would be installing. We would bring the power supplies into the sides up in here. This breaker, like a breaker that you have seen in electrical class, hooks on with feet on the back side here, and it's going to bring that power down into two screws that are located on the load side of that switch itself. And then we'll use some liquid tight connectors to come out, and we'll go to our outdoor unit and power the outdoor unit in that way. Here's an example of the outdoor unit. The disconnect is sitting there on the wall, and then we are going to run liquid tight down and up into the outdoor unit. I always like to run the liquid tight along with the line set. So as I'm coming straight down this wall, I'll come straight down the wall. I'll jump over to the line set as best I can, making it look smooth and nice, and then come into that outdoor unit, strapping it as I go to make it look like a nice and clean installation. Here's just another example of the disconnect switch. Disconnect switch sitting on the wall. Okay, they're going to run that wire down, hopefully where the line set's coming in, over to the line set, and then up into the outdoor unit, making it a nice, clean transition from the disconnect box into the outdoor unit that's sitting there. As far as our low voltage wiring is concerned, we are going to be running 18 gauge wire. Now, I can tell you for a fact that I've never ever had a problem running an 18 gauge wire with the voltage drop on that system. The graph that we are showing you right here is the recommended size control wire for a particular amount of a run for that wire. You can see that what they're talking about here is 18 gauge wire, good for 3 amps, but they only want you to run that in a total length of 20 feet. That ain't never going to happen in any installation that we're dealing with. I've ran 18 gauge wire over 100 feet. It has provided for us a, a the voltage drop uh, has not been significant enough for that 18 gauge wire to affect the operating system of it. But if we were going to follow manufacturer's recommended sizes for those particular units, then I would have to run some 14 gauge wire for that. And you're talking expense here for a control wire. So that's why we usually don't see a lot of control wires ran in 14 gauge. Although the graph that I am showing you here happens to be from a Rheem distributor telling us that if we run a significant run of um, a significant run length and run for a control wire, that we need to up the actual size of that control wire. We can see down here, do not use control wire smaller than 18 gauge control wire for these particular units. Like I said before, never really had a problem with these particular units running an 18 gauge control wire. So what we're looking at here is the outdoor unit, the thermostat, and then the indoor unit. The way that you are going to run your control wires is every connection that you're going to make for it has to be made inside the indoor unit. I've seen a lot of my students out there use the thermostat as the connection point for the outdoor unit and the indoor unit. It works for my class, but it doesn't work for the field because this thermostat is going to be sitting on a wall somewhere 20, 30 feet away. Okay. We're not going to take the wires that are coming from the outdoor unit and run them into that thermostat. That's not the way we're going to do it. Because I want accessibility to those wires. So I'm going to take those wires and I'm going to run those wires from the outdoor unit all the way into the indoor unit. The second thing I'm going to do is I'm going to take the thermostat wires and I'm going to run them down and I'm going to run them into the indoor unit in a nice, clean way. The purpose for that is so that I can quickly check with my multimeter or by touching wires together what system components should be running or should not be running at that particular time. It's hard for me to pull the thermostat off the wall to get behind there to check those wires on that particular unit. So I never ever want to make my connections at the thermostat. I want to make all of my low voltage connections at the indoor unit. Every time you see a dashed line, like we are seeing here, that means that is field installed wiring. Whether that's low voltage or high voltage dashed lines are wiring that the technician in the field is going to be accomplishing for that particular unit. Typical wiring for a single stage air conditioning unit with a gas heater or an oil heater that's hooked up to it. All the connections are going to be made on the indoor unit. R is for power, W is for heat, G is for fan. Now we'll try our best to write fan out. Okay, Y is the cooling. Okay, so what happens here is power comes up from the indoor unit into the thermostat. The thermostat's going to receive that 24 volt power in there. What is a thermostat? A thermostat is a switching device, and that's all it is. After the thermostat says, hey, our building's getting too hot, it's going to send out power. And this is sequence of operation. It's going to send out power through the G terminal. It's going to send out power through the Y terminal. Y terminal is going to come into the indoor unit, typically into a furnace control board. Once the furnace control board sees the Y terminal that it gets a 24-volt signal, it will kick on the fan more than likely. It also, we are going to jumper in parallel out to the outdoor unit, just like that. And then what happens is we'll power a contactor out here. Contactor will complete the circuit back to the common on the indoor unit. So 2 wires to the outdoor unit on a single stage air conditioner. Some thermostats will send power out through the G terminal, okay? And that power will run back to the board, and then the board will kick on the furnace. The W terminal is not used for the air conditioning, as that is heat only. Okay, so what we have here is your basic air conditioner with an air handler or electric strip heat. So electric heat, this is the typical sub base that you will see on the indoor unit. You'll have the red wire. Red wire will run up to the thermostat, but that power is coming from that indoor unit, from the transformer that's a step-down transformer on the indoor unit. The white wire is going to be for the heating, but we're not in heating, so you guys just took that class. So we're going to go to the G wire right here, and the G wire is for the indoor fan. Now, most air conditioning systems, the G wire will actually be energized when the cooling is going to be energized. Then the board will decide whether to turn on the G, or if it gets a Y signal, then it will turn on the high speed or the cooling speed, whatever one it is. The yellow, and I want you guys to notice this because a lot of people make this mistake when they're installing these systems. That yellow wire ends up inside on the indoor unit. And after it ends up on the inside, we'll take a wire nut and we'll run that unit to the outdoor unit sitting right there. So that's typically how it goes. After that, you're going to have a brown wire that's going to come back, or a blue wire that's going to come back as you're completing circuit for the outdoor unit. And that's typically how your low voltage will be hooked up. So what we have here is a 2-stage unit, a 2-stage air conditioning unit. Notice that we have an indoor unit, an air handler, a 2-stage thermostat, and then a 2-stage outdoor unit. So first stage is going to be Y1. That's going to be your cooling. Notice that these are connections right here, and they're basically taking this wire out to the outdoor unit. Make all of your connections on the indoor unit. So the R is coming up to the thermostat. Sequence of operation tells us that the thermostat is just a switching device. Okay, coming up there. We also have a wire running out to the condensing unit. This one must have a board that needs to be powered. So that's why the R is going out there. The R does not turn on the compressor or the outdoor fan. And I need you to understand that. There must be a board on the outdoor unit on this one that requires 24-volt power to operate, either for a safety or other means of operation. But we're getting all that 24 volts from our indoor unit. And that's coming to it from the R terminal. The next thing the thermostat's going to do, it's going to say, hey, we need cooling. The first stage cooling will be energized. It will send 24 volts to the indoor unit from the thermostat, and then it will send 24 volts to the outdoor unit. This will turn on the indoor fan, and it will also turn on the outdoor unit. After a certain degree has passed, or a certain amount of time, and the indoor unit has not satisfied, the thermostat then will kick on the second stage cooling, which is indicated by that Y2. Y2 will come down. It will power on the indoor unit, and it will power the Y2 on the outdoor unit, providing it with second stage. So either the compressor has a 2-stage solenoid on it, or it has two speeds on it. The two speed compressors have kind of went along the wayside. We are now dealing with solenoid valves on our systems themselves. G will be energized as well, telling the indoor unit to kick on. We see the thermostat has a common, so the common will go to the common on the indoor unit. Plus, we need to bring a common back from the outdoor unit so that those systems will operate perfectly fine. Now, that is a two-stage unit. The next thing we're going to be looking at is a communicating system. Now, usually communicating systems are four wires. Some of them are labeled 1, 2, 3, 4. Some of them are labeled 1, 2, RC. But however they're labeled, you're gonna have to hook up the wires to the exact terminals on these communicating units, or they will not communicate with each other. The thermostat communicates with the indoor unit. The indoor unit communicates with the outdoor unit. With communicating systems, there's a lot of things that we can do to look at different aspects of the system airflow, capacity, subcooling, superheat, discharge pressure, suction pressure. All of these things are going to be built into these units because they're very sophisticated. I like to look at communicating systems as well as gas modulating systems as units that have a gas pedal on them. If they need to go faster, the compressor will ramp up and go faster. If we need to provide more heat, the furnace will ramp up and provide more heat. We need to slow down really far, we can do that, and the system will work just fine. So hook these terminals up exactly like they are listed. R and C are the power wires, 1 and 2 are the communicating wires. And there's a lot of things that we can do with these systems, a lot of systems that we can run very, very well. So running your line sets, what I always like to do is run my liquid line and my suction line together. And these are the systems, these are the lines that are going to be running from the outdoor unit into the indoor unit. So our liquid line should never be touching our suction line, and you want to try to avoid at any cost any of these copper, which is copper is a very soft very soft metal. And if it was to touch anything that was harder than it and it was to vibrate up next against it, the copper would actually deteriorate away, and we would end up with a hole in that copper. So I like the picture. I like the way that they're depicting how you should run that particular unit. Take a look that we are wrapping both the communication wire, the low voltage, not the high voltage, the liquid line and the suction line, and we're bundling them together to run them from one location to another, from the outdoor unit to where the indoor unit actually is. So that's going to be nice. Some people use tape, some people use wire ties. Your preference, whatever you want to do, just make sure it looks nice and neat, and that it's not it doesn't look like a bundle that's just been thrown together. So the communication wire or the control wire or the low voltage wire will be ran along with that line set itself. So when we talk about line length or length of line from the indoor unit to the outdoor unit, we're going to want to measure. At some point, we're going to have to add some refrigerant to this system if our line goes over a certain amount of allowable. Every system's different. Read the manuals, and then you'll understand what you need to do with the line set for that particular one. We have certain variances, like we can't go vertically too far high, or we can't go horizontally too far, or we can't go uh, vertically down too far, or we're going to end up messing with the capacities that these systems can produce, ending up getting flash gas inside of our liquid line and a lot more other things that could go wrong because the manufacturer said, hey, you can't go over a certain length. Otherwise, the system's not going to operate like we're telling you it's going to operate. So line length from the outdoor unit to the indoor unit. Some other things that we have to consider is for this particular unit, and I can't remember if I drew this from a ream or a train, but this particular system has a standard line set of 150 maximum feet that this system can run, with a 50 feet max vertical change of that unit. And if we were going to go down, it has a 50 feet max change going down to the evaporator as well. So you got to watch for the certain line lengths of this. Now we're going to measure with the tape measure these particular lengths of this line set as we're going with the installation. Now, if you do have a line set that's coming to you, you want to make sure that when you go to insulate it, that you are separating out the liquid line and the suction line. Never run that insulation around it so that liquid line's touching that suction line. That is not the correct way to install the suction line insulation. Remember, our suction line will sweat because it's below the dew point of the air. It's cold and it's going to condensate, so that's why we need to insulate it. When we go into supporting our actual line set, I suggest you use some sort of plastic hanger, so it doesn't eat its way through that copper. You're going to want to do that a maximum of 8 feet, but I would like to see that closer together every 5 feet or so on that line set, so it's not drooping. It must be ran in such a way where the suction line is going to be pitched towards the outdoor unit so that that oil can return to that outdoor unit so we don't lose compressors due to that. But securing the vapor line from the joist using isolation or strapping or some other form of vibration elimination to keep that line set from transferring noise inside of the building itself. And when we look at actually going through a wall, I'm going to sleeve this line. So here's my line set. I want to take that line set and I want to sleeve it with some sort of plastic pipe and run it through that plastic pipe, so I'm not touching any wood or any material that can rot away, just in case the vapor line does leak a little bit of vapor through it into that environment. It's also going to give me a nice area to seal up around, and then I want to fill up that cavity that I'm running my liquid line, my control voltage, and possibly my high voltage out through that hole. It's going to allow me a nice area to put a sealant on that pipe as it's coming through. I'm going to want to fill this cavity as well. If after the installation of it, after everything's okay, so we don't get any air coming into the house or the environment that way. Most of our units can be multi-positional. This is an air handler for a ream. We're looking at it. We got to look at it, ensure the retaining channel is fully engaged in the chain rail, such as these guys up in here. And it's going to hold that coil in place. Read the manual and find out how you're going to flip these coils.
Auxiliary drain connection, 3/4 inch FEMA pipe thread, NPT style, horizontal application only. Primary drain connection, 3/4 female pipe thread, NPT. Auxiliary drain connection, 3/4 inch female pipe thread.
Get party.
So the liquid line connection is going to be hooked up to this unit as well as the vapor line connection. The condensate drain is probably one of the more important aspects of these units. We need to drain away that water that we're getting from the air as we're cooling it down. So one of the side effects of cooling air down is we're going to condense that air on the evaporator surface, condense that moisture on the evaporator surface. And we need to take that drain and move that water away from that evaporator coil down a drain somewhere away from the unit. So good field practice is required to insulate that condensate line as it's coming off of the indoor unit at least 10 feet away, especially if you're in an attic or an area where you have high moisture. So that line will actually sweat and will cause damage to surrounding drywall, surrounding wood, or other types of materials that can be destroyed by that condensation. There is a minimum trap depth that we want, and the purpose of this is we want to keep that water within the trap, and especially on our air handling units. Our air handling units will actually suck air up through that line if it is trapped inappropriately. So 3-inch minimum trap from the outlet of the condensate of the indoor unit to give that enough area in there to hold that water, so we do not suck air up there. If we were to suck air up into the indoor unit, it would actually back the condensate up and it would overflow outside of the indoor unit, causing damage possibly to downstairs or to the environment that it's actually in. So another reason that we want to run that condensate line is we want to pitch it in such a way that we don't start to develop any mold or mildew growing on that particular drain pan. That can be detrimental to our customers, but also it can smell so that they would smell a foul smell whenever the air conditioner kicked on, and that's not what we want. We want to use PVC piping, which is non-corrosive, so we're not going to deal with ferrous metal piping, no black iron, no galvanized on our indoor units. Try to stick with PVC piping. Lines should be trapped like we discussed on the previous slide, 1/8 to 1/4 inch per fall per foot, and then insulate that at least 10 feet if you're in an attic situation or a situation where that condensate line will run into hotter air, and it would have the chance to condense moisture on the PVC pipe. The indoor unit, the evaporator is mounted securely inside of that unit. We're going to try to isolate that unit from any of the structure by rubber pads, spring isolators, canvas duct connectors, trying to break down that vibration coming off of it so our customers don't hear that particular unit running, especially when those fans get a little dirty and the blower wheel becomes unbalanced. Unit also must be installed in a way that it's easily accessible to us to service the evaporator, the blower, and the electrical components that are on it. So try not to run the line set directly in front of this unit, but run it in a way where you are going to be the one servicing this particular unit. Now your condensate drain, you might not have a natural fall to that condensate drain, so or an easy way to put that condensate out. So we'll put a condensate pump in this unit so that we can take that condensate that comes into it and pump it out to a different location. These are also serviceable. We need to take these apart every time we're cleaning an air conditioner and make sure that we are putting control tabs on the inside of them so we're not dealing with algae or mold or any other sort of nasty critters on the inside of these things. They do have maximum lift height, so just be careful of that. Read the manual on it, and you'll figure out how to install these particular condensates on these units. So here's a installation that I have done at a local thrift store. A couple of things I want you to notice: that the ductwork is nice and straight. The condensate drain that we have put on there is going to be pumping the condensate from the indoor unit out into the outside in a place where it's going to drain away relatively easily without causing any damage. But one thing I want you to pay particular close attention to is the auxiliary drain pan that's underneath this particular unit. This drain pan was there for the purpose of catching overflow of the condensate if it was ever to plug up the main drain on the top portion of it. But also notice that I have placed a piece of particle board or plywood underneath of it to stiffen up that auxiliary drain pan. A lot of installers will just take this unistrut and will go straight across and will support that piece of flexible plastic panning across these two. Now, once that water starts to flow into that pan up in here, it will become heavy and it will bow right in the middle of that condensate overflow auxiliary pan, and it will drip water out of the pan because it is curved. So then you'll get the water coming down. So the way to prevent this from happening is to go ahead and put a piece of plywood like I have done underneath that pan, stiffens it up and doesn't let it bow, so that if there is any overflow or drippage from the evaporator coil, that it will flow directly back into the condensate pump and will pump that condensate out into the outdoors. Here's another installation that I've done. Notice that the installation is nice and neat. I have clipped these wires. It looks like about every foot as I'm coming down this particular unit. You want your installations to look nice. You want your installations to look professional. If they don't look that way and you have a problem with the unit, the customer is going to be a lot more picky about what they're going to say to you, rather than when you come down to a unit that looks like this and everything looks professional in that unit. Uh, they'll just assume sometimes that maybe it wasn't your fault, maybe it was something that just went bad on the particular unit. But a nice unit alleviates a lot of problems within a system itself. Drain lines are coming down from the evaporator. We're going to tie into the furnace drain here, and notice that I have left an air gap on these furnace condensate drains so that if the condensate from the evaporator was to drain backwards into the furnace, that it would have an outlet to go to before it would flood the secondary heat exchanger up and possibly ruin pressure switches that are inside the gas furnace itself. Now these lines are going to come down to a condensate pump. We're going to take that and we're going to pump it up and out into a drain that we have a little further away from this furnace installation. Notice the ductwork is nice and straight, wiring's nice and straight, disconnect switches and switches for the pump. All of this was installed by me. Looking at the gas line, nice and straight coming down. A nice installation. Customers shouldn't have very many things to say about this, if anything was to go wrong with it. So here's an attic installation that I have done. Notice that I have put a platform down for the auxiliary drain pan. And that auxiliary drain pan, and we notice a couple of safety devices on there. One's right there, and I'll highlight it in yellow. That is called a auxiliary drain pan overflow switch. So if the auxiliary drain pan was to overflow, this switch would shut off the air conditioner to prevent any more condensation from getting to that point. Right before it overflows is when the switch should go off on the unit itself. Condensate drain running here, and this is going to be running to the outside of the house. Notice that the condensate drain for the auxiliary drain pan is not hooked in with the primary drain. The reason for this is if the primary drain does plug up and we have tied these two drains together, then the primary drain will overflow into the secondary drain or the auxiliary drain pan, causing it to overflow in some way, shape, or form. So we want to take that condensate drain to a location where the customer will notice that the auxiliary drain pan is overflowing and the auxiliary drain pan has water in it and is dripping that water out. Now, this is going to save us from from damage from the downstairs unit. I mean, the damage to the drywall that's underneath this unit since it is an attic installation. The next slide, we're going to take a closer look at that overflow switch that's on that drain pan. So as water is coming up into the drain pan, this switch, if it gets too full, will shut off the air conditioner so that the air conditioner will not run anymore and it will not be dumping any more condensation into the overflow switch. This is also going to alert the customer that there is an issue with the air conditioner when they don't have any cooling inside of their apartment or their house. Now, this is going to be tied into, there's a couple of different ways we can do this. These wires are running over. I can tie them to the R and I can hook it in series with the R so it breaks that. I prefer not to do it that way. I will probably come across with the Y terminal from the indoor unit and then hook it in series with the Y terminal on that indoor unit. So it shuts off the outdoor unit, but the indoor unit is continuously running. The customer will notice that there's a problem and we'll give you a call to fix that solution, to fix that problem on that particular unit. So when we look at places that we want to install the outdoor unit, there are a couple of places that we want to avoid. We do not want to put an air conditioner beside the bedrooms. This is true for air conditioning. This is true for heat pumps. The noise of the unit might infiltrate into the walls, and then the occupants of that place would find out that the noise of the air conditioner is going to be very disturbing. Well, the occupants will end up not enjoying the noise that the air conditioner is going to produce. In today's world, our air conditioners are a lot quieter than they used to be, so this doesn't tend to be a problem, but we want to try to avoid being near a bedroom just in case that unit would bug those individuals while they're sleeping. Keep all vegetation away from the unit, at least a foot. I've seen people plant things right up against it because they don't want the ugliness of the units, especially today. These things are 5 feet tall, horrible looking on the sides of the buildings. But keep the shrubbery away. We need that airflow to come in. As far as the access panel, getting into the electrical box, we want 3 feet in front of that unit so that we can get in there and easily work. And then above a unit, and this is depicting a ream type of unit, we want a 5 foot unrestricted area above that unit. Another area that we want to watch for is runoff from the roof onto the condensing unit itself. We want to try to avoid that rain. Now, it's just going to create a water issue. I know it's outside. It's just going to create some sort of condensation issue on the inside, moisture with the boards, the contactors, and other pieces of equipment out there. It's just going to deteriorate a lot sooner than what we would like to see that unit last 15 to 20 years. It's going to eat it away a lot easier. So minimum from the wall, minimum from shrubbery, good airflow around that unit is what we're looking for. Now here's a nice install, nice clearance around the actual unit itself. Line set is ran nice and tight against the wall, and then out to the outdoor unit. Good airflow coming around it. Disconnect whip is ran along with it. I'd like to see that guy a little tighter, looking at it in the picture this way, but for the most part, a decent install for this condensing unit that we're going to be running. Another install. So this is one, we're drilling a hole, 2-inch hole into the side of the building. We're going to sleeve it with a PVC pipe, and then we're going to insert that into there. Okay, getting back to it. We've got a line set that's running into that. There, I'm going to drill the hole through there. It's a 2-inch hole into the side of the building. I'm going to insert a 2-inch PVC pipe, and then I'm going to insert the control wire, the liquid line, and the suction line through that hole. nice and straight going into the indoor unit. And then we'll go ahead and we'll braze that up. Now, as far as the pressure testing and as far as the microns that we need to drop this unit down to, you're going to have to read the manuals on these particular units because they're talking about pulling vacuums and breaking them and pulling them and breaking them. They're talking about triple vacuum on these units. So you're going to have to really, really pay attention to the manual and what these manufacturers are wanting from you, the installer, for this particular unit. So whole hogs, cordless drills are going to be used on these. Try to use hole saws when you're going through vinyl. Get you an initial hole, and then put the hole hogs on there, which is just chews up wood really well to get us into that environment to run those line sets. As far as the condensing unit and the installation of it, we're going to be looking at runoff from the roof. Should not land on the unit. Locate in the shade. Better for heat transfer if the sun's not beating on that guy. Away from tree sap, berries, blooming plants, and these things are going to grow up inside of that particular unit itself. Units should not be noticeable. That's why individuals like to put shrubs around it, but it's kind of avoidable, not avoidable now because of the size of these units. Located away from bedroom windows, located away from gas meters, 5 feet, electric meters, 5 feet, and the flue gas coming out from the unit at least 5 feet is what we're looking at for that particular unit. So connecting that outdoor unit to the indoor unit, we're going to run that line set nice and straight. I'm not quite sure. I do not think I've ran that line set yet for that indoor unit. Looks like something that we're going to be doing later on. But for that particular unit, we'll go ahead and run it nice and straight and then hook it up. The way that you straighten out a coiled line set is to take it from the outside of the line set, step on it, and then walk your way, rolling that line set as you go. And that's going to give you a nice straight line set that's not going to kink on that unit itself. The next couple slides, we're going to go into actually brazing, pressure testing, vacuuming these particular units. This was on a ream unit that we're going to be going into. So pay very close attention to what these units want. I've been doing a little bit of studying on our mini split applications. And when I've been reading the manuals on those guys, they're talking about triple evacuation. So it's something that we got to be very careful of to actually do what the manufacturers are requesting us to do for those particular units. So a lot of these slides are very self-explanatory. So be certain both valves, both refrigerant valves on the outdoor unit are shut off at the service ports themselves. Remove the caps from them, remove the Schrader cores from them. And that's being depicted here by this picture. These are service valves, liquid service valve, suction service valve. Take the caps off, take the Schraders out. And before we start brazing on this particular unit, we want to protect it from the heat that we're going to be placing on this copper because we don't want it to damage those things. And that's why we're removing them. Excessive heat can actually damage these valves, especially the neoprene gaskets that are on the inside of them. Clean the inside of the pipe. Clean the inside of the pipe. Clean the outside of the fitting. You can use flux if you want. You don't need to when you're brazing copper to copper. But if you desire to use that, fine. I'd say from a manufacturing standpoint that we want to try to avoid any chemicals that are going to be inside there, even though, brazing flux does help prevent the oxidation when we start to heat these guys up. Keep any chips, debris, metal fragments out of the pipe. We don't want anything on the inside of it. These orifices in these metering devices are very, very small and they will plug up. So be sure that you're keeping dirt and any foreign material out of this pipe as you are hooking it up. We want to use type L copper. It's a thicker copper. It's ACR copper. Braze the connection with a minimum 5% silver braze. Nothing less than that. That's not what we're going to have to do. So whenever you're brazing, make sure you're using 5% minimum. There are some really cheap brazes out there, but make sure you're using the correct brazing. Look at the cover of the braze, and it will tell you the silver quantity that's in that particular tube. Copper, when you're doing steel to brass, you want a higher silver content. 15% minimum on that.
It's just dropping.
So some more things that we want to try to accomplish with this is you want to wrap the valve very, very well. Otherwise, you're going to burn up the gaskets on the service valve. It's going to leak out the top of the cap when you go to take those caps off. You also want to be flowing dry nitrogen through those lines. Now, what this is going to do, it's going to go through the indoor unit and come back out. And as we are flowing that dry nitrogen through there, we are preventing the formation of oxidation. We are displacing all the oxygen out of the inside of the pipe, and then we are causing it nitrogen to be in there and filled up so that we do not form scale on the inside of these pipes. Once again, scale's a problem, forms acid, blocks up metering devices. It's not a good thing. So flowing nitrogen is very, very important for us. There are tools out there that will specifically flow the correct amount of nitrogen for you. When we came out of school 25 years ago, they always told us, flow some nitrogen until it starts to feel it on your hair, on the back of your arm. You can do that. I'd buy the tools so that you're getting the correct CF, getting the correct flow of nitrogen through that particular system. Try not to overpressurize the pipe because you will blow out the solder instead of keeping it from flowing in. We will teach you the techniques of brazing. We will give you the practice that you need for that application here at the university, and I hope that you guys perfect it. I do not like Zoom lock. I do not like the push button types of moving. Push button. I do not like that type of system out there because you're taking a skill away from individuals. Yes, they don't have to purge nitrogen, but you're going to run into a situation where you're going to have to braze. It's a skill that you should learn, and time will tell whether the leak locks or the rigid pro presses are going to pan out to be a good idea in our field. We'll see how long those gaskets do last within that field. So as you are brazing, making sure that we're filling that entire cavity up with our braze rod, making sure that we're keeping that towel or that moist rag wet with a spray bottle so that we do not hurt that valve itself. So after you get done brazing on that unit, we want to wipe it down and try to cool it off as fast as we can. And then after we've cooled that down and we've pressure checked it, it's time to install the Schraders back in the system, depending on how we want to pull vacuums or that. I know the manufacturers want us to install the cores But there's a lot of good tools out there now that are allowing us to pull faster vacuums, quicker vacuums, and better vacuums using vacuum rated hoses, valve core removers, and micron gauges that are going to give us decay levels on them after holding that vacuum for a particular amount of time. So reinstalling the Schrader valve cores might be something you do at this point, but it also might be something that we put off until we've actually pulled a proper vacuum on the particular system. So what we're dealing with here is after we get done brazing those line sets, and you're going to have to check the manual to make sure this is off of a ream type of unit that you have to look at the particular manuals because we have different ways that we want to pressure test these systems. For this particular one, what they want us to do is pressurize it to 150 psi and do that pressure test. Let it stand for 15 minutes, 30 minutes, an hour, just to make sure that we don't have any leaks on our joints. And then what we're going to do is spray down the joints to make sure we don't have no leaks on it. The pressure test is going to tell you whether or not you're going to have a leak on it. And if we get any drop in the pressure test, then we need to find out where it's coming from. Mini splits are a different monster. If you're looking at the pressure testing those, you might have to open up the LEVs on those, and then because there's no port on a Mitsubishi unit when it comes to that. So you have to look at specific items such as that. And I just encourage you as you are installing units out there to read the manuals on them on there. What we want to do also is in our installation process, we don't want that vapor line, we don't want that liquid line to contact each other because vibrations will cause leaks within that system. So the insulation that's around that system, around that pipe, will keep it separated from there. But anytime that insulation is off, we want to make sure that our liquid line or any type of metal that is harder than that copper does not touch it because it will result in heat transfer, but also vibrations will cause a leak later on down that system's line. The vapor line must be insulated on this system. Mini splits are different, like I said before, where both lines are on the low side of your system. Both of those lines need to be insulated, but the vapor line on a split type traditional air conditioner needs to be insulated because it's going to be a foam type of insulation that's going to prevent the moisture from getting in and causing condensation. That condensation is going to be really absorbing heat from the environment, but also it's going to be there to, if we do have condensation, it could end up damaging some of the structure if we don't end up insulating these lines properly. Armaflex insulation, Robotex insulation are satisfactory installations for this purpose. We'll show you examples in the classroom as we go along. Additional insulation may be required for runs that are longer than that. After we get done pressure testing the system, checking for a leak, insulating the lines, we want to pull this thing into a 500 micron setting. Now, different systems out there are going to have you do triple evacuations or nitrogen breaks on the vacuum, and all this is doing is we're trying to drive that moisture out of that line set so that we can have a system that is free of moisture and of air. After we pull it down into a certain micron level, and you're going to have to check the manufacturers on this. This ream manufacturer says 500 microns. I've ran into Trane manufacturers that talked about 250 microns, and I've read up on Mitsubishi's that talk about bringing that system down into 1,000 microns, breaking that vacuum with nitrogen, bringing it down to 500 microns, breaking it with nitrogen, and then bringing it down deeply into the micron level that we want. And this is going to ensure that all the air and all the moisture is out of these systems. The vacuum pump must be connected to both the low and the high side. We have different types of systems out there that'll pull really quick vacuums for us, especially on a clean system such as this. And if you're dealing with a system that has already been open to the atmosphere, oil and refrigerant in that line set. It might take us longer to pull those vacuums down, but a clean system, man, so fast to pull those vacuums. After we get done vacuuming it down to the proper level, we're going to do a decay, a vacuum decay on this. We're going to hold it for 15 minutes. We're going to watch that vacuum, and that vacuum should not increase more than 100 microns over a period of 10 to 15 minutes. And you're really going to watch this because this is going to indicate whether you have a small leak on the system. If it continues to rise and rise and rise, we have a leak. But if it comes up and it settles out at a certain micron level, then we're good to go into our next step. And the next step would be to open up the valves on that system. So once we have adequately vacuumed the system, pressure tested the system, we can open up these valves on the outdoor unit. And what this will do is release the refrigerant that the manufacturer has put on the inside of the unit and let it go into the system so that we're ready for this system to actually operate. We're going to use a 3/16 and a 5/16 hex wrench. They do make special tools out there that make this a lot faster. But anyway, this is what we're going to be doing counterclockwise. Take it all the way to the end, and it's going to be fully open. And your Schrader valves should have been installed by this point. After you get done putting refrigerant in there, and like I said, there's different ways that we can do this, and we'll teach you about these guys when we get to it. So using the correct drain hole is important when you're using a horizontal. Read the manuals, like I said again, so that you understand where the proper drains are going to be. There's overflows on these as well. Some jurisdictions require that you have an overflow protection or an overflow shutoff valve on these, and that's it just depends on where you live in. But read the manual and find out which drains that you guys are going to be using for this particular ream unit. We have the bottom one down here, which we're going to be using. These other ones up here are the overflows. If we take it in a horizontal position, we're looking at the water is going to be draining onto the auxiliary drain pan and draining down into the bottom down here, overflow, and then the actual unit is going to be sitting there. So here's your actual drain. Here's your overflow drain, and then the water is going to flow in this direction. We're going to be making sure that we trap these units so we don't have to worry about any air being sucked up those lines. It's going to it'd suck air up and it'd keep water in the drain pan, overflow the drain pan eventually. So watch that on your installations. The last thing that we're going to be discussing will be the location of the TXV bulb if you guys happen to have a TXV. For this ream manufacturer, and like I said, go back to your manufacturers and read the manuals, and they'll tell you better where to put these guys. But we're looking at a 10 o'clock or a 2 o'clock area for the on top of the suction line. So this is the vapor suction line, and we want to install that particular sensing bulb on that suction line at a 10 or a 2 for according to the ream. This is going to sense how much liquid refrigerant we have in the system, and it's going to let that TXV adjust to the superheat values that are on it. Well, guys, that's it for me. Oh, one other thing I wanted to point out about this, if we looked at those suction lines, and kind of looks like a Mickey Mouse to me with the ears, and if you want to think of it like that, then yeah, put the sensing bulb at a 2 o'clock position or a 10 o'clock position over here, and then you will not go wrong with the positioning of that liquid line. If we're dealing with a larger liquid line, 7/8 or larger, we want to go to the bottom of that liquid line right down in here so that we get a proper sensing of the liquid that's in that refrigerant. Guys, I hope you enjoyed the PowerPoint. That's the end of the show. Take this and do your quizzes, and you guys will do fine on it. Good luck on that. Have a good day.